We're live.
Welcome everyone to day 2 of the OpenCog conference. Yesterday we had some rather deep discussions in terms of the use case of Atomspace, and today we're going to take our discussions and then ending with Linus's interesting keynote on the actual Atomspace itself. And today we're going to begin kind of talking about the next generation of OpenCog, which we are now terming OpenCog Hyperon. I'm going to hand it over to the illustrious Ben Goertzel once again, who's going to give a tentative sketch of this next generation of the OpenCog architecture.
Yeah, thanks a lot, Matt. So, yeah, yesterday, as Matt said, we had some discussion of what's there now in OpenCog in my keynote and in Linus's keynote, and we had some in-depth consideration of some of the work being done now using the current version of OpenCog for machine reasoning on bioinformatics data, genomics data, biontologies, and so forth. Now, that work has been interesting both for the value and insight it's giving regarding biological systems, and also for what it's revealing about the strengths and weaknesses of the current OpenCog platform as a body of software. And the same was true of the work we did earlier using OpenCog to control the Sophia robot. I mean, that was really interesting, and we were able to get more flexibility in Sophia's responses and interactions than Hanson Robotics was getting with the other alternative software systems that it was using on Sophia. On the other hand, the work using OpenCog to control Sophia, it also taught us some things about what aspects were less than optimal in the OpenCog implementation that we were working with. And there's always been these two aspects of OpenCog, one being the conceptual and theoretical approach to general intelligence, and the other being the specific software design used to realize that approach to general intelligence. And in the past, we've had various naming conventions for this that have never really taken off. I mean, for a while we were calling OpenCog the software system, and OpenCog Prime or Cog Prime or Prime AGI were various names we were toying with for the AGI theory and design that was being implemented on top of OpenCog. And we had even the idea that you could use OpenCog platform, you could use it to implement a lot of other different AI systems. You could use OpenCog platform to implement NARS, non-axiomatic reasoning system, as designed by Pei Wang. You could use the OpenCog platform to implement a biologically realistic neural network. You could use a platform for a lot of things besides the specific AGI theory laid out in the book Engineering General Intelligence. Now, as it's happened, the primary use of OpenCog has been to do work along the lines of the specific AGI theory laid out in the Engineering General Intelligence and related papers. OpenCog didn't actually take off as a platform for general implementation of a whole bunch of other AGI approaches, although I think on a technical level it could have been used that way. But in using OpenCog platform, both to flesh out our AGI ideas and to do various practical things like analyze biology data and control Sophia, do financial prediction, and a whole bunch of other back-end applications that my colleagues and I have built with OpenCog. We've learned a lot about both how to bring the AGI theory ideas we were pursuing into reality, and about, what properties you really want for a software platform to underpin the realization of these ideas. So out of all that, a bunch of us involved with OpenCog came to the conclusion over the last year or so that it really was time to do a major refactoring of OpenCog, and possibly a rewrite from the ground up of core components like the Atomspace, which Linus talked about in his keynote yesterday. I mean, exactly which parts get rebuilt from the ground up versus which things can be reused from existing OpenCog implementation is something that is not yet decided with certainty. But to me, the important thing is that we're undergoing now a process of, look at the requirements, understand what we really need to do for AGI at the human level, and also what we need to do to step toward AGI through a series of progressively broader and broader narrow AGI applications. And then based on those requirements, I mean, we make a decision regarding what to replace or what to modify. And so we're now undertaking this process, and the focus of today's part of the OpenCogCon is really to open up the topic. So I'm gonna give an overview of some of my thoughts and some of the discussions we've had in the team on this next generation of OpenCog and the process of building a new and better OpenCog system. And then a number of my colleagues, so Alexey Potapov, will go in some depth on thoughts about, building a new pattern matcher and a new Atomese language for the new version of OpenCog. And Cassio Pennachin, who was the chief architect of the original OpenCog version, I mean, before Linus came in and took on the lead developer role. Even Cassio will talk about some thinking him and Andres-san and others have been doing about the distributed aspect of the Atomspace and how to make a massively scalable Atomspace that can run on a huge number of machines in RAM and with persistent stores and so forth. And we'll also hear a bit about work being done to take OpenCog's Moses tool, which is a probabilistic evolutionary programming framework that's currently separate from the Atomspace, and work that's being done now, led by Kasim Ibrahim and Neil Geisweiler, to pull that into the Atomspace. And that's interesting as one among many, AI innovations that we've been sort of held back from doing by scalability and performance issues with the current OpenCog framework, and that I think we can proceed forward with more rapidly and effectively with the new version of OpenCog that we're now designing. So let me pause for a moment to initiate screen sharing here.
We can see it.
All right. So, we went through a few options regarding names for new versions of OpenCog. I mean, we'd been informally talking about Atomese 2 and OpenCog 2, and that was sort of both serious and kind of an inside joke, because of course the current OpenCog version is not 1.0. I mean, that Atomspace, you could argue Atomspace maybe 1.0 in a way. That's a relatively mature piece of software. OpenCog as a whole has a variety of components at a variety of levels of maturity. I mean, some have been used in commercial projects, and others are really more at the research phase. So eventually we decided that numbers are passe, and if you can have trusty tar Linux version and the Mountain Lion operating system. We can replace numbers with names. And I figured since we have atoms at the base of OpenCog Atomspace, which are nodes and hypergraph links, then we may as well have some elementary particles. And the physicists of the world have given us a lot of funky elementary particles to choose from. I liked Hyperon is kind of an obscure particle, but it had the resonance with hypergraph. So the version of OpenCog that we're now engaged in designing is OpenCog Hyperon, and then inspired by Arnold Schwarzenegger in the Terminator. Sometime in the future, we may have OpenCog Tachyon that can go back in time and solve all our problems retroactively. And so jumping into it a bit, the goal with the OpenCog Hyperon, with the next phase, the next version of OpenCog, I mean, the goal is the same as with the original version of OpenCog. I mean, the goal is AGI at the human level, and then a platform to get from the AGI at a human level, even beyond human level. And we're thinking a lot now about the transition from here to human level AGI through narrow AGI systems that are highly capable of doing specific things in specific vertical markets, but with increasing levels of generality of understanding. And having worked on OpenCog for transfer learning and generalization and bio AI, having used OpenCog to control Sophia, and having done so much R&D experimenting with the current OpenCog system, we just have a way better idea of what the requirements are and what strategies work and don't work than we did in 2008 when designing the OpenCog original system, or in 2001 where the original Atomspace code was written that grew into the OpenCog Atomspace. So as I highlighted in my keynote yesterday, I mean, there's a lot of technical issues we're wrestling with. I think the biggest, like, super high level requirements we want to be sure we achieve with OpenCog Hyperon that have been suboptimally present in the prior OpenCog version. I mean, we need scalability of various sorts, distributed processing, and speed of real-time or near real-time interaction, and speed of interfacing with external software tools. We need something that's easier for application developers to deal with, to use to build various narrow AGI applications. And of course, usability for folks developing the core platform is one thing. Usability for folks using the platform and applications is another thing. Both need to be thought about, and they can have different particular characteristics. And then we want to develop OpenCog Hyperon from the beginning with some cool demonstrable applications that then get better and better and show more and more achievement as more and more is fleshed out, to avoid the situation we've been in with OpenCog in the first version, which is those of us who are deep into it know there's so many amazing insights being generated and so many cool things being done there, but most of them have been realized in a way that you have to be pretty deep into this system to understand what's going on and why it's interesting. I mean, there's always going to be some of that aspect, but we want to pay attention more to demonstrability from the get-go. And I think the timing is good to make a push on all these things, both in the sense that there's a broader community interested in AGI now than there was in 2008 or 2001 or even a couple years ago, but also that supporting software tools are so much stronger. I mean, when I first tried to make a distributed hypergraph knowledge store for AIs in the WebMind AI system in the late 1990s, I mean, we're using Java 1.1 across a bunch of quad processor Dell PCs that were in a closet of our office in New York, and you had to roll everything yourself, right? I mean, now we have a whole bunch of scalable distributed key value stores, vector stores, and so forth, and there's a lot of infrastructure tools that can be used to make these things less time consuming and painful to achieve than in the past. So I think it's a really good time to be building something like OpenCog Hyperon. I think the AGI requirements and the core algorithms and structures we want to realize with this system, these remain largely the same as with the original OpenCog version, and the Engineering General Intelligence parts 1 and 2. Those books remain the best guide. Certainly, there's a bunch of other intellectual contributions that has come up. Linus has introduced some really deep ideas from the theory of sheaves that tie in with the link grammar and syntax and semantics of language and how to learn them. Alexey Potapov has introduced some deep ideas related to probabilistic programming and algorithmic information. So we've had a bunch of theoretical insights, which are in papers that are posted online in Archive and AGI conference proceedings and elsewhere. I would say, while these are significant innovations with some genuinely profound new ideas they're also consistent and coherent with what is in the Engineering General Intelligence books. So I think we're still going in the same direction in terms of AGI theory, so that if you're interested to understand theoretical background, these materials are a place to start. Then there's more recent papers also to look at. I had a blog post a couple months ago which linked to a bunch of my own papers aiming more at the theoretical side, trying to understand sort of what is general intelligence. And all this is there as background in terms of the higher level requirements. And we don't even necessarily talk about this higher level background that much in practical work on OpenCog, because those of us in the center of the OpenCog project have been sort of ensconced in these ideas for so long. But for people coming new into the project, it's important to understand there's this broad sort of cognitive systems theory, algorithmic information theory, probabilistic theory of mind background underlying all the concrete software engineering stuff that we're discussing. And many of us who've been in this project for a while take this theory background sort of for granted, and we're focusing more on nitty-gritty issues now, because we sort of already internalized how all this theory of what a mind is and what a human-like mind is, how all this theory connects with certain software structures. So to give just a few minutes of service to the higher level theory stuff before plunging into OpenCog Hyper on the design and requirement stuff. I mean, the part of the high level view here is, a mind is a self-organizing system of patterns. It's engaged in recognizing patterns in itself and its environment, including critically but not exclusively patterns regarding what impact its actions will have, like patterns regarding which actions will achieve which goals in which context, for example. And it's also engaged in building and building new patterns in itself and its environment based on patterns it's recognized. So there's a goal achievement aspect, not necessarily strictly maximizing expected reward, but trying to make certain patterns appear in the world in the hypothesized future of the AI system. And there's also an open-ended intelligence where the system's just sort of crystallizing the emergence of various patterns in a way that may cause its goals to evolve and change, because part of development, as distinguished from learning, is that in a developing AI system, which all of us are, our top level goals can even self-organize and change over time as we're seeking to maximize them. So that's all very, very general. I mean, you can also look at how human-like minds specifically manifest this general logic of cognition. I mean, human-like minds have a bunch of aspects that cognitive psychology has identified over a long period of empirical and theoretical study and simulation modeling. I mean, we have long-term memory, we have working memory, which has a number of different specific aspects, like phonological buffer and spatial workspace, and we have specific parts of the brain and mind oriented toward motivation and toward action selection, which are grounded in basal ganglia in the brain. There's emotional responses, which in the brain are mediated by limbic system and amygdala, and the emotional responses modulate action selection and motivation, and also guide memory access in a quite powerful way. And we then have deliberative decision-making processes, which are tied in with the sort of moving focus of attention, which is sometimes called consciousness or reflective consciousness. And there's specific parts of the human brain and mind dealing with language. There's specific parts dealing with reflexive reaction. And you can view all this as the way the general properties of general intelligence are manifested in general intelligence, with this moderately specific problem of controlling a human-like body in an environment composed of, solid objects that you can move around in, and other human-like systems that you have a shared environment with. And I think it's important to understand that to achieve human-level AGI effectively, you can't just have a different system in each of the boxes in the wiring diagram I showed before. Like you can't just take one long-term memory module, one metacognition module, one working memory module, and whatever, and have them as isolated boxes and wire them together where they're just sending simple inputs and outputs between them. I think that the processes carrying out each of these functions have to be able to expose their intermediate states to each other. And that's how you can get cognitive synergy, where the algorithms and structures involved in each of the core cognitive functions underlying human-style general intelligence, the things inside each of these boxes can help each other out when they get stuck in a way that is contextualized on their internal state. And this notion of cognitive synergy, it's been formalized using category theory and some related ideas. There's a paper I had on arXiv on that a few years ago, which is not in the engineering general intelligence book. It's more recent theoretical development. You can also look at, how is cognitive synergy specifically manifested in terms of human-like AI systems, in terms of the specific requirements that being a human puts on you. And I argued in a paper called the Embodied Communication Prior some years ago, might have been 2011 or something. I argued that the particular types of memory in the human-like mind and the types of learning in the human-like mind, they can be traced back largely to the requirements of being a mind that has to communicate with other similar minds in a shared physical world, and about shared goals to be achieved in that shared physical world. And the train of thought here is pretty similar to what Yoshua Bengio described in his paper, The Consciousness Prior, last year. And I guess Consciousness Prior is a whizzier name than Embodied Communication Prior. But I have my own thoughts about consciousness, which I'm not going to get into here, but I also prefer to distinguish the philosophy of consciousness from the practicalities of engineering general intelligent systems. So I think the notion of embodied communication prior is similar to Bengio's notion of consciousness prior. It's like, what's the prior on the perception, generalization, and cognition, which is relevant to bias a general purpose AGI system to be a human-like AGI system. I think viewing it as an embodied communication prior is probably more useful than viewing it as a consciousness prior. And all this thinking gives a theoretical grounding for a bunch of what we're doing in OpenCog, where you can look at, based on the needs to carry out embodied communication with shared goals in a shared environment with other minds. I mean, you then get to the need for memory of sensations, memory of shared episodes based on your shared experience with other minds, shared attention. So you need attentional memory. You do need some sort of reinforcement-based learning, so that you can learn from your experience regarding simple actions. And you need to be able to learn and remember facts and beliefs, which are sort of persistent patterns in the shared environment. So from all this theory, you come out with the idea that you need, declarative, sensory, episodic, attentional, and procedural memory. And you need these different types of memory to have a shared state. And you need learning, which is somewhat somewhat biased or specialized or primed for handling each of these particular types of memories. So learning that's particularly good at learning facts and beliefs, learning that's particularly good at learning patterns and sensory data, learning that's particularly good at learning procedures and so forth. And this brings us into OpenCog, where, you know, PLN, probabilistic logic, is one way of doing learning that works especially well with declarative knowledge. Moses evolutionary program learning is one way of learning that's particularly good for procedural knowledge. You know, deep neural nets of various sorts are a mode of learning that's particularly good at recognizing patterns in sensory data. So you do need these kinds of learning that are in a way biased or partly specialized to certain types of memory. On the other hand, they all need to work together really well. And one way to do that is to have a common meta-representational fabric, which is the OpenCog Atomspace and the OpenCog design. So the OpenCog Atomspace is designed to serve the representational needs of all the types of memory that are required for human-like intelligence, and for the intermediate states of all the kinds of learning associated with all these types of memory needed to achieve human-like general intelligence. And this finally leads us up to the undertaking we're looking at now. And, you know, this diagram is different than the diagrams on the previous pages. And of course, I showed one diagram that was aimed to show the synergy of different cognitive processes acting in a common atom space. A diagram before that aimed to show the different higher level processes involved in the action of a human-like mind as it engages in the world with a long-term memory, working memory, and so forth. Those were more cognitive architecture diagrams. Now this is closer to a high-level software architecture diagram. I mean, still at a fairly conceptual level of abstraction. But what you can see here, we have a distributed atom space, which Cassio is going to talk about today. Then the distributed atom space goes across many, many different machines. Then on a particular machine where the thinking work is done, you have a local cache atom space, which is more like what the current OpenCog atom space does. So in current OpenCog system, what we're thinking of as the atom space, I'm now viewing as a local cache of a distributed atom space. And we now have a Postgres backing store, which could be distributed because Postgres can be distributed. The current Postgres backing store is a sort of early prototype of a distributed atom space, but as Cassio will outline, we need to go way beyond that. And if you're managing a really effective distributed atom space with multiple coordinated local caches, you need some fairly sophisticated middleware for managing all these local caches. We've been looking at Apache Ignite as one possible source of that middleware, but there are certainly other options. Attention allocation, which is a cognitive process managed in the current OpenCog system by ECAN, economic attention networks. This also serves a sort of infrastructural role, because attention allocation is the process that tells, you know, when something needs to pop out of persistent store and into RAM, or when it needs to be replicated from one local cache atom space to another one. So there are these cognitive decisions about how the distributed OpenCog mind should be allocating its attention, and these cognitive decisions, they interplay subtly with the distributed processing decisions of, you know, moving nodes and links in a distributed atom space from one place to another, or when to keep a copy of a node or link, or a bunch of nodes and links in multiple atom spaces. How closely do the different versions of two nodes or two sub hypergraphs need to be coordinated with each other? Or can they drift a little? So there's interesting cases where the cognitive aspect interoperates and interplays with the distributed systems aspect. We can also use OpenCog Pattern Miner to recognize patterns in the distributed atom space. And Shujing Ke had a prototype of a distributed OpenCog Pattern Miner a number of years ago, which he used to mine patterns in the distributed atom space representing atoms gotten from video game worlds. And the hypergraph to vector stuff that Manhin and Debbie talked about yesterday, this can also be used in our distributed atom space to make a huge embedding vector index of everything in a distributed atom space. You know, we then have Atomese language interpreter, and this ties in with what Alexey will talk about. In the current OpenCog system, the pattern matcher is the workhorse, and it's not just a static pattern matcher. It's a dynamic pattern matcher that really does bits and pieces of reasoning and functional logic program interpretation. It's an amazing, masterful piece of code created in large part by Linus Vepstas with help by Neil Geisweiler and a few other people here and there. Now, we're looking at a major restructuring of that, where static pattern matching is deployed in a simple but highly scalable way across the distributed atom space, and some of the other in-depth stuff that's done inside the current pattern matcher is then extracted from the pattern matcher and put into the Atomese language. So the default way of working with OpenCog now is you're using mostly Scheme, sometimes Python or Haskell, mostly Scheme to wrap up calls to the Atomspace API and calls to the pattern matcher. So it's a mix of manipulation of pattern matching on hypergraphs via the Atomspace APIs and pattern matcher API with Scheme scripting. And we're thinking about sort of reorganizing that so the pattern matcher becomes simpler, but orient toward distributed scalability. And a lot of what's done in Scheme now is just done in the new Atomese 2 language. And then there's a line of thinking like, how do you make this really usable for application developers? I mean, we're looking at making sort of application specific APIs or DSLs within Atomese language. And this ties in with a lot of what Alexey and Vitaly and some of his collaborators in the SingularityNET St. Petersburg office have been thinking about. Then using this Atomese language, we then have the AI, which is where the really interesting stuff happens, right? You have PLN, probabilistic logic. You have Atomspace Moses, which Neil will talk about doing probabilistic program learning in Atomspace. And you also have Atomese code that interfaces with external tools calling into PyTorch or TensorFlow and so forth. And there's some interesting issues there regarding how deeply do we wire tensors into the atom space? I mean, to what extent is a vector or a tensor a sort of a native type for the new Atomese language? I mean, now we can wrap up in grounded schema nodes in the current OpenCog system. We can wrap up calls into PyTorch or other external frameworks for doing scalable neural net training or other tensor manipulations. And Alexey and Vitaly, Sergey and his team in St. Petersburg has done some pretty sophisticated things there with cognitive module networks, as they've published in some papers over the last few years. But we're thinking to make that marriage even a little deeper, embedding tensors perhaps more deeply as native types in new Atomese language, which should lead to more efficient and flexible interfacing with deep neural net and other floating point libraries. But again, there's a lot of work to be done there. So this diagram is, I think, reasonably valid as a reflection of our current thinking. On the other hand, there are many question marks and things to be resolved in each aspect. And I'll go fairly quickly through this Atomese 2 part of my deck because Alexey is going to go over it in more depth and in his own way. I mean, here's just an example of what Atomese looks like from the developer's point of view right now. So I mean, this is from a system we made in conjunction with Cisco for identifying jaywalking. I mean, you had object and event recognition coming out of deep neural networks looking at various street cameras. And then we had Atomese that identified various patterns of interaction between people, cars, and so forth. And you can see here bind link, type variable link, and link, inheritance link, concept nodes, variable nodes. So there's various sort of nodes and links and various sorts of relationships. And what you do now as an OpenCog developer in practice, I mean, you can create and inspect nodes like this directly using the scheme APIs. And of course, you can also write AI agents in C++, Scheme, Python, and so forth that are themselves interfacing with node and link constructs like this and creating and reading them in their native hypergraph form in the atom space without having to spill them out into textual form. So some key questions that we're going to be talking about during the rest of this the next few hours of this event. I mean, okay, Atomese as the formal language, which is a representation of the nodes and links inside the Atomspace and their different types. I mean, what is this formal language? I mean, how are we formalizing the nodes and links in this hypergraph and their types and weights? I mean, a formal language is not the only way to look at the set of types and weights in a hypergraph meta-representational system, but it's one useful way to look at it. And then if you view this set of node and link types and their interrelationships as a formal language, how are you interpreting this formal language? Like when you have executable or evaluable content in this Atomspace, how do you execute or evaluate it? Do you always interpret it? Do you compile it to a more efficient form for repeated evaluation or execution? And to what extent do we use this to create formalized sub-languages, either say DSLs for end user to use for simple creation of various practical applications, or sub-languages used to make, say, automated program learning or automated reasoning of different types easier? And Atomese in a way is an internal language. It's a language of mind of the OpenCog system, but it also can have a syntactically sugared version for human developers to use, which could be a general syntactically sugared version, and then versions with special syntactic sugar for particular applications. So how does the language actually look? And then we get into issues regarding the data store. I mean, the local data store for the knowledge hypergraph or metagraph, if you want to use an even broader term that encompasses links pointing to whole subgraphs and links pointing to links and so forth. I mean, how do we design this local cache store, which needs very heavy usage? How do you design this distributed store? Then the Atomese libraries, I mean, this is where something like PLN logic comes in. And a lot of that is Atomese content now, which could be ported over to a new Atomspace. I mean, in theory, just because you rebuild the guts of the Atomspace doesn't mean all the AI code we have now has to be rewritten, because a lot of the AI code is just Atomese content. I mean, it's implication links and it's grounded schema nodes. It's nodes and links embodying different learning and reasoning rules and methods. And a lot of that could just be imported to a new Atomspace with a different implementation. Some of it you might want to rewrite to better make use of cool features, though, put into the new Atomese. And then we get into the question of how do you interoperate all this and other AI tools out there. And this is where OpenCog Hyperon interfaces with SingularityNET also, right? Because SingularityNET is a platform for interoperating a bunch of different AI systems. It could be written by different people based on totally different AI paradigms. And I mean, how does an OpenCog talk to all the other AIs other people have put in this SingularityNET in a way that's efficient and can even sometimes involve shared state as shared state or shared access to large knowledge stores, as well as simplistic back and forth according to APIs. So those are all big questions. We're not going to answer them all in the next few years. We're going to tell you something about how we're thinking about those questions and what we're doing with an aim toward resolving them. Thinking about Atomese 2 in particular, some of the questions that come up are, how do we achieve simple compact representation of the various atom types that are used now inside PLN and Moses and vision processing and so forth? How do we have a compact representation inside the Atomspace of external entities? Like how do you represent a torch computation graph, for example, effectively inside OpenCog Atomspace? How do you represent Mathematica if you were to use it as a symbolic math library? How do you interface with that appropriately inside the Atomspace in a way that lets you, for example, compose or algebraically manipulate the OpenCog representation of different computations being done and interacted with in these external computing frameworks? And regarding pattern matching, how do you break down the pattern matching process into sub-processes that can be explicitly controlled and manipulated by reflective cognition within the OpenCog system? How do you make this all work consistently with concurrent and distributed processing and in a near real-time control context like you need for a robotics application? And then on top of that, how do you make this relatively simple for a developer who hasn't been spending 30 years working toward AGI to tweak this and improve it for their own application, as well as to use it for their own application. So obviously, none of this is especially simple. On the other hand, we've been playing around and prototyping in this domain for a long time. So we're fortunate to have an amazing team that actually has a strong intuitive sense regarding what can work and what can't for all these issues. But we certainly need more people to help think through these things as well as to do the implementation. And on the Atomese 2 programming language side, I'd say one of the biggest challenges, and also one of the saving graces that makes some things more tractable than they would be otherwise, it's the fact that, you know, a lot of the mechanics of Atomese interpretation doesn't have to be that fast because accessing the knowledge base is so slow. Like, this is very different than something like TensorFlow, which is spending all its time crunching numbers and doing multiplications and divisions on big vectors and matrices. Here, the vast majority of the runtime is taken doing pattern matching queries, basically looking for stuff in the Atomspace, either local cache or distributed, or doing updates and applying hypergraph rewrite rules across the Atomspace. So the fact that the vast majority of time is spent on these Atomspace interactions, this, on the one hand, it means you got to try like hell to optimize these Atomspace interactions, which we're going to talk about. On the other hand, it also means that it's kind of okay if doing like type inheritance or type conversions or these other back-end programming language manipulations are not that fast because there's this other really stuff anyway. And that's a saving grace, because some of the fancy things with higher order types and gradual typing and so forth, I mean, no one knows how to do those right now fast enough that you'd want to say write you know, a word processor or a computer operating system in a gradually typed higher order functional language. Like doing these type manipulations is still kind of too slow and awkward for that. On the other hand, if it's in a language that you're designing to spend most of its time doing these knowledge graph interactions anyway, you don't care. You don't need to optimize the gradual type inheritance to the level you would if you're making a language to write an OS or a word processor. And I think pattern matching, and Alexey will talk about this, needs to be optimized heavily in this approach, and many other things don't need to be optimized as obsessively. And this pattern matching is hard. Like it's a lot more general than the pattern matching that, say, Neo4j is doing in the Cypher language. I mean, here we need to be able to match a query term against a whole sub-hypergraph, and we need to match against atoms representing variables, and it could be variables that are variables standing for other variables, standing for other variables. I mean, there's a lot of representational subtlety here, even in static pattern matching, without getting into inference. And beyond static pattern matching, then in the Atomese language wrapping around pattern matching, we need to be able to define and manipulate new atoms. But I've come to think we also need to think a lot about how to use Atomese 2 to define and manipulate type systems. And this gets into the Agda language, which I've spent a bit of time playing with. And I feel about Agda like that's at the same level Haskell was when I started playing with Haskell in 1993, 94, like back before GHC, back before monads. You could see Haskell was the future, right? It was too slow to be used for general purpose programming, but embodied insights that weren't there in other programming language. And Agda is a bit similar now. It's too slow. I'm not going to write a Sophia robot controller in Agda. On the other hand, Agda lets you write programs by just specifying complex higher order types. And then when the Agda theorem prover investigates whether there's anything inhabiting that type, it's executing the program. And I think there's some interesting thinking there behind Agda that we can use in thinking about Atomese 2. And part of that comes down to you need to be able to specify, you know, custom dependent type systems in Atomese 2, so that when a reasoning engine is doing type checking, some of the cognition is happening that way. So a type system needs to be a first class citizen, and this leads to thinking about gradual typing. Like right now in OpenCog, Atomspace typing is pretty loosey-goosey. Like you can create an atom with a custom type that you define, and there's sort of no, you can define type inheritance and type relationships and type valued variables. You can do anything you want, but on the other hand, it's not efficient to do these type manipulations at all, and there's no systematic way to enforce consistency and coherency. It's all DIY for the creator of the nodes and links and their types. And we need to retain some of this looseness, but we need to be more rigorous and more efficient. And gradual typing is one potential way to do that we're exploring, where a node or link could have a type, or it could have no type. It could have a type according to one of a set of different type systems. And then you need type checkers according to the various specific type systems in there. And you also need an overall gradual typing framework that deals with both typed and untyped things. And in the last few years, there's been fantastic progress in the creation of, reasonably efficient gradual typing systems for higher order, dependently, gradually typed functional programming languages. And this is amazing. Like, this totally didn't exist in 2008. I mean, this is a whole level of advance in type system, type checking design and functional programming language design, which we can then exploit in Atomspace 2.0. And there's some deep theoretical connections here that I don't have time to go fully into. But if you look at a gradual typing system, this is mapped by the Curry-Howard correspondence between logics and programming languages. That's mapped into a paraconsistent logic, which is a logic that can maintain contradictions. So being able to have a type system that can let something be untyped with multiple possible types at any point in time, this is in a way morphic to having a logical predicate or proposition that could have multiple different competing truth values based on different evidence sets. So in PLN, we've always known we had to deal with the case where the AGI system had multiple conflicting bodies of evidence and didn't yet decide which of the conflicting bodies of evidence to believe, like who's lying, which sensor was faulty. You still need to be able to do logical reasoning, even if you have conflicting bodies of evidence and you haven't decided which observations to throw out yet. You still need to be able to do your probabilistic logic. And that pushes PLN into being a certain type of paraconsistent logic. In a similar way, in a gradually typed program execution framework, you may have nodes and links which haven't been assigned a type yet because you don't know what type to assign them. And you may have the system invent its own new type system later on that requires the reassignation of the type of something. You still need to be able to do program interpretation, compilation, and execution in that framework. Interestingly, these are the same problem, as you can see, with certain category theoretic mappings. And so what this means is that PLN logic is actually a perfect way to do reasoning about an atom space with a gradual typing system, which means that if we introduce gradual typing in OpenCog Hyperon, we already have in many ways the reasoning engine needed to do reflective meta learning and inference on this gradually typed atom space, which is quite cool. And then you can dig deeper, as I did in a paper for AGI 20 conference that is posted on Archive, and there's a talk in underline.io from the AGI 20 conference. I had a paper on what kind of programming language is suitable for AGI, and I go over some references in the literature there in probabilistic type systems, linear logic type systems that take into account intrinsically the resource usage in an inference, and dependent type systems, and then various restrictions on type inheritance and type inference that make it more practically tractable to deal with these very abstract types. So I think, we do have some notions of what kinds of type systems are needed to give really elegant and efficient representations of the learning algorithms in current OpenCog in an OpenCog Hyperon that has a more sophisticated typing framework. On the other hand, as a general requirement for the new atom space, I mean, what we need is to have a playground for experimenting with variations on type systems. Because, I mean, while I've done some deep dives here, I'm sure we haven't gotten everything right. Another paper I had in AGI 20 conference, which I'm not going to talk about at all here, but I started thinking about, the inner implementation of interpretation on this sort of higher order gradual type system. And one approach, which is used inside the Haskell interpreters and compilers, is super combinators. So I started thinking about, how do you tweak the super combinator approach for optimally efficient interpretation and compilation of this sort of system? And that was a paper on combinatorial decision DAG. So there's there's a lot of knowledge in the functional programming literature already. There's also some new ground to be broken there. Now, some specific areas I'm thinking about that maybe we can plunge into in discussions a little later. I mean, my oldest son, Zarathustra, is doing his PhD now in machine learning for automated theorem proving in Prague. So due to him, I've gotten a little tighter into the automated theorem proving community. And the problems they're looking at there for automating math are really very similar to things we're looking at in trying to automate common sense reasoning in OpenCog. They're also largely the same as the problems you have in trying to automate meta reasoning and learning new reasoning rules and reasoning about how to reason. So, I mean, but looking at automated theorem proving and the requirements you need to make OpenCog Hyperon, effectively interact with a theorem prover like E or Isabel or Koch, and provide a level of generalization and abstraction to complement the low-level sort of quantifier munging of these automated theorem provers. I mean, this is one application area that's interesting to look at in terms of requirements for OpenCog Hyperon, and this will drive directly to the requirement that the system needs to be able to robustly reason about its own type systems, which is then equivalent to robustly reasoning about its own reasoning and learning algorithms. Another requirement that's interesting to think about is algorithmic chemistry. Like, you want to be able to have little programs, procedural knowledge living in the Atomspace, where what they do is take another little program as input and produce another little program as output. And this becomes a sort of primordial soup of programs that rewrite programs to make other programs. And when a program relies on background knowledge to help it transform program A into program B, when C relies on background knowledge to help it transform A into B, then that background knowledge is serving as a catalyst, right? So you have an analog of catalysis relations in chemistry and autocatalytic sets in chemistry in this soup of inter-rewriting programs. And again, this has been developed back to the 90s with algorithmic chemistry for computational creativity and automatic program learning. We need to be able to do this on huge scale. This is how we get a system that can create and imagine even better than humans. And it's not too hard to write code to do this. In the current OpenCog system, it would just be insanely slow. I mean, you need rapid Atomese execution across a large distributed atom space with a bunch of different interconnected local caches to really do the experimentation here. And if you look at what GPUs and multi-GPU server farms and so on have done for deep neural nets, they took a bunch of stuff that people have been playing with for many decades, and just by adding scale, they made it suddenly work way better. Well, the same is going to be true for algorithmic chemistry. I mean, Walter Fontana was playing with this in the 90s, so was I and a bunch of others. Once we have a distributed scalable atom space with rapid Atomese execution across that distributed atom space, you're going to find stuff like algorithmic chemistry. It's going to need some tweaks and improvements. You're going to find this suddenly works and starts yielding superhuman computational creativity, and that the main missing ingredient was a sufficiently large and efficiently operating program soup to do the algorithmic chemistry in, which is what we're building now. So in the last minute or two, because I'm a bit over time, I want to just point at some of the environments we're thinking about for evaluating and experimenting with the OpenCog Hyperon. And this gets into the demonstrability high-level requirement that I mentioned at the beginning. I mean, we want to have OpenCog Hyperon doing some cool stuff right from the beginning, so that it's easy for us to see how progress is going, easy for people to engage with it. So we went over yesterday a bunch the bio AI use case. I think this is a valuable one, partly because we have a large and well curated atom space already that we're experimenting with the current version of OpenCog. So we want that same stuff to keep on working and work even better. We've also gone back to some work that we were doing in, I guess, 2011, 12, 13 with the current version of OpenCog. We were controlling these little guys in a Minecraft-like world. I mean, back then the Minecraft-like world was running in Unity 3D, but we had these little video game agents with different goals, like get food, get energy, be safe, have some social interaction, and they were learning and planning their interactions in this simplistic world using OpenPSI motivational system and using logical reasoning frameworks. There was a lot of hacks we had to do. This was led by Shai Jemois and Huang Deheng back quite a while ago at Hong Kong PolyU. There was a lot of hacks we had to do to get all this stuff to work, man. We can do this way, way better with the current OpenCog system with PLN and the pattern miner, and we'll be able to do it even better with OpenCog Hyperon. But I mean, now you have OpenAI Gym and you have Microsoft Project Malmo. You have a bunch of cooler frameworks for interacting with Minecraft-like worlds. But I still believe this is an interesting experimental playground, although it may be too simplistic to lead to the human level AGI. And of course, there's the Sophia robot, which we're going to continue to work with Hanson Robotics on these and other humanoid robots, which is a different sort of playground. I mean, it's dealing with scalable data and huge data streams coming in. And, you know, compared to when we were working with Sophia before, now there's a moving base which rolls around, and there's hands that can pick things up and put things down. So the Hanson Robotics hardware has advanced, so we can use this more as an interactive perception action system. And you know, controlling Sophia as a theatrical and commercial system is one thing, and it is always going to involve a bunch of application specific scripting and coding, but you can use these same robots in a different way in your research lab for more of a robot preschool type thing. I mean, you can look at child IQ tests, which are designed for kids up to 7. I mean, these involved answering basic questions like, if I cut an apple in half, how many pieces will I have? Can you piece together these blocks into a comprehensible shape? Like, which of these pictures fits in the box? So it's quite interesting to take robots like Sophia and run them through child IQ type tests. Not so much with a view of proving the robot has a high IQ. This would be too easy to hack in a specialized way, but just in the vein of exploring the IQ of exploring the intelligence of your early stage AGI systems in the same sort of way that human psychologists are exploring the intelligence of their young children with their emerging intelligences. So I think if we look between Minecraft type worlds and Sophia type robots and then bio AI, I mean, we have 3 application areas, each with their own strengths and weaknesses, which can be used to drive development of OpenCog Hyperon system. And we're now collaborating with Hanson Robotics and others on some commercial applications here. I mean, we can't have commercial applications of OpenCog Hyperon yet, which does not yet exist except at the conceptual and design level. However, we've spun off a company from SingularityNET called TrueAGI AI, which is sort of building the wrappers and the knowledge bases and some proprietary application code, which is aimed at interfacing OpenCog type systems with robots and embedded devices. So TrueAGI AI as a business would license Mind as a service to Hanson Robotics and other robotics companies. It would also license Mind as a service to, say, handset makers who want smart virtual assistants inside their mobile phones. But TrueAGI's Mind as a service code on the back end would call on OpenCog for its intelligence. And initially it could call on the current OpenCog system, but the whole idea is TrueAGI will contribute to building out OpenCog Hyperon next generation architecture. And once Hyperon is there, that will really make the provision of Mind as a service to robots and embedded devices, you know, highly practical and powerful. And I think, you know, we're very committed to open source with a very liberal and general licenses for OpenCog on into the future, so that anyone can use them commercially, non-commercially, for whatever research they want. Just as SingularityNET, which is part of the infrastructure for the distributed OpenCog Hyperon system, that's free and open and fully decentralized. On the other hand, commercial development is going to help drive this, just as commercial companies like Red Hat have helped to drive the development of Linux as an OpenCog system. So TrueAGI as a commercial company driving delivery of mind as a service to robots and smart devices, I think this commercial company building on SingularityNET can help give some of what's needed to OpenCog Hyperon as an OpenCog initiative, though by no means all, any more than Red Hat gave all that was needed for the development of Linux. So yeah, I think that is by no means all I had to say, but it's all I'm going to take time to say right now. And we have a panel later on this morning, so I think I will defer questions and discussion to that panel to avoid running any further overtime than we already have. I think we should run straight into the great Alexey Potapov now, and we'll keep a list of the questions people have been asking so that we can make the panel primarily a group Q&A session.
Thanks, Ben. Hello?
Hello.
I said thanks, Ben, for that
You're welcome,
introduction. Did you want, I think there's a really good question I could ask, or should we just skip to Alexey?
If you have one really good question, maybe we could take it. Why not?
Yeah, so I would say it's really, I'm combining two questions regarding the first mind architecture that you presented at the very beginning, and then the second one, which is the OpenCog conceptual architecture. And so it's really two questions in one, which is what is the source for the high-level mind architecture, and then the same person asked, I think that person mentioned that didn't see how the components of the OpenCog conceptual architecture mapped into that high-level mind architecture.
Yeah, I mean that is a really good question, and the answer is a bit lengthy. So there's I'm trying to find the paper where we went into that in great detail. So there was a book, Theoretical Foundations of Artificial General Intelligence, edited by myself and Pei Wang. And Matt, I think you and I wrote that paper, actually. We had a paper that addressed precisely that point. I mean, what we did there, we gave a sort of integrated architecture diagram that glued together many different cognitive architectures in AI, and we tried specifically to map the sort of wiring diagram of all the parts of the human mind into the pieces of OpenCog and LIDA and a few other cognitive architectures. So that, I don't know, Matt, can you dig up the title of that paper?
It might take me a little while.
The paper was called The Architecture of Human-like General Intelligence by Ben Goertzel, Matt Eclay, and Jared Wigmore, who is now Jade O'Neill.
Oh, okay. Yeah.
The Architecture of Human-like General Intelligence in the book
I remember it now.
Theoretical Foundations of AGI. And I'm pointing that out not to dodge the question, but just because it would take half an hour to answer the question, going through everything in that paper. Because what we did there is we took that high level diagram that I showed, and we had like 7 other sub diagrams, like one sub diagram for long-term memory, one sub diagram for working memory, one sub diagram for perception, and then when you go to the sub diagrams with one diagram for each box in that high level diagram, then the connections actually emerge. And I may dig that up so I can show it during the Q&A section later if it's an interesting.
I think that would make sense.
Interesting to more people.
Okay, and with that, then why don't we just transition to Alexey Potapov, who will begin talking on Atomese 2. Some thoughts.
Yeah. So Alexey Potapov is the leader currently of SingularityNET's St. Petersburg office, which is doing a bunch of OpenCog stuff and a bunch of other kinds of work in SingularityNET platform and some commercial AI work. But I was extremely thrilled to pull Alexey into OpenCog and SingularityNET because I'd been reading his papers on AGI for quite some time before we started working together. And it was clear that our perspectives on AGI were extremely similar conceptually at core, and also in terms of some habits of thinking. We're both kind of mathematical oriented. On the other hand, he was often coming from a complementary direction. Like I was probabilistic logic, he was probabilistic programming, right? So I think there was a lot of overlap and also some interesting differences. And we'll see the same thing in what he's going to present today regarding his own thinking on Atomese 2.0. So yeah, we're honored to have Alexey, the leading light of Russian AGI here today. Thanks, Alexey.
Thanks, Ben, for the introduction. Hi, everyone. As it was mentioned, let me start sharing my screen. Okay, can you see it? Yes, it was mentioned the topic of my talk, some thoughts on Atomese 2 or Atomese OpenCog Hyperon. And it's really not all thoughts, but some thoughts, because there are very many aspects to the Atomese Hyperon design, which will be difficult to cover in a limited amount of time. And for example, Ben mentioned that our team was working on symbolic, sub-symbolic integration like cognets, which were implemented by Anatoly, or grounded object nodes, which were implemented by Vitaly. But we covered these things in our some previous papers, blog posts, and presentations. So I will focus today on something which wasn't covered in some public materials. So first of all, I'd like to give some motivation for OpenCog Hyperon, and there are several groups of sources of motivation, like improvements for important use cases, scaling, design improvements, and AGI R&D. Of course, everything in these directions is going on in the current OpenCog, and it's really cool that it is consistently improving and so on. But as we will see, there are many different intersecting issues which are just simpler to build from scratch. And in this case, we will not need to have some sort of backward compatibility of these core modifications and the existing OpenCog. So this existing OpenCog is still being developed and will be developed further, and OpenCog Hyperon will be developed in parallel from scratch, and we will see what happens. So basically, what are some important use cases, as Ben mentioned, and as we have had this first day of OpenCogCon, one of the most important cases we are considering now is Bio AI, and it has really huge ontologies integrated one atom space, and we need to do both reasoning and pattern mining over this huge knowledge base. And for example, even if we are doing pattern mining on a small part of bioatom space, it already takes like 64 gigabytes of RAM, and we really need some scaling. So there are many other particular things which we encounter while working on BioAI, like graph embeddings for guiding inference, custom atom types with knowledge and rules about types, support for multiple overlapping ontologies, and so on. Another large source of motivation is something embodied, something grounded, like virtual assistants, which gather information from different external services and devices, Internet of Things, smart homes, smart cities, robot control, and so on. And these use cases, they also require distributed episodic memory. For example, if we are talking about virtual assistants, then it can be a shared episodic memory, like there is a common information, say restaurants all around the world, or some city, and so on. And we need to query this information or knowledge using both symbolic and sub-symbolic custom indexing, and reasoning-driven querying, grounded reasoning, and so on. It's really interesting to have something like language to Atomese in all these applications, because users will prefer to formulate queries in natural language, and they can be mapped into pattern matcher or unified rule engine queries, and so on. These applications also require a sort of cognitive cycle or real-time concurrent non-blocking inference. We have OpenPsy, for example, right now in OpenCog, but it's sort of perpendicular to the unified rule engine. They can somehow be combined, but still all this inference reasoning calls will be sort of blocking. So we have a lot of motivation from these important use cases. And of course, we have some requirements for scaling, as already was mentioned before. And of course, we need some design improvements, because working with Atomspace, Atomese, and OpenCog for years gave us a lot of insights how things can be organized. So we would like to have a clear model behind the core language, because the semantics of current Atomese language is sort of just implemented in the code, but there is no some formal specification of what is being done and how it is being done by the Atomese interpreter. We would like to have types as first-class objects definable in Atomese or Atomspace itself. We would like to have type checking and so on. We would like to have modularity or extensibility, which we will discuss a little bit later in more detail. And of course, we are interested in AGI, and from the AGI perspective, what is the most important thing if we just want to generalize everything is an efficient and scalable but general enough inference. And many different research projects using OpenCog are aimed at different sort of cognitive synergy between different components and meta reasoning and so on. But well, there is a very good and very interesting trend in the current OpenCog version towards bringing everything in Atomese, because before different different components like pattern miner, like Moses, were just implemented separately and were interfaced with each other in a sort of shallow way. And recently, Neil has ported pattern miner and Moses to the unified rule engine rules, and it now looks closer to the possible sort of automatic, not hand-coded achievement of cognitive synergy. But there are still many external tools or methods which are not yet implemented in OpenCog, which we would like also to be implementable in Atomese. And as we will see, it's not that easy. So if we consider all these issues, as I said, they are incrementally being solved within the current version of OpenCog, and that's really good. But they're interacting, and they need a systematic solution. For example, if we take pattern matcher, then it acts as a graph DB query engine, Atomese interpreter, and basic step of reasoning. And different requirements can be put to all of these users of pattern matcher, and we need to satisfy these requirements at once altogether. And we can ask some questions like, is it possible to make querying efficient over a distributed atom space? What is the semantics of Atomese language? Where is the border between Atomese interpreting, pattern matching, and reasoning? And how can we reuse pattern matching in other inference engines? So yeah, we would like to have a clear systematic solutions to different problems at once, or as we will see, not maybe a just complete solution, but a possibility to study different ways of doing inference, for example. So let's start from the knowledge graphs. Indeed, it's a very important thing right now. And yesterday there was a question, why do we need Atomspace and Atomese if there are such things as Neo4j? And indeed, at first glance, pattern matcher is actually doing exactly the same thing as Neo4j query engine. But well, as Linus already mentioned, this solution, like Atomese language or pattern matcher, appeared much earlier, and in a certain sense, it was behind its time, and graph databases started to flourish a little bit later. But besides this, there is a really large difference between what pattern matcher is doing and what graph DB query engines are doing, because pattern matcher works on hypergraphs, and they are not that easily mappable on plane graphs. And if we do this in a naive way, then Neo4j will not be efficient on these queries. And pattern matcher actually does much more. It does not just static pattern matching, but dynamic pattern matching, and it also acts as a single step of reasoning and a sort of Atomese interpreter. So what's about reasoning? Once again, with bind links and pattern matching, we can do single step reasoning, and the unified rule engine can chain these steps to form inference trees and find such branches which will lead to a desirable solution, as using backward chaining or forward chaining. And that's really cool that we can use this basic steps to build on top of them something more complicated and AGI-ish. But there is a sort of inconsistency. So if you consider pattern matcher as a GraphDB querying engine, then we would write down something like this. So these are sort of domain-specific rules. We say that we need to query this graph, and if we find it, we will infer this as a result or conclusion, and so on. But it's actually not a recommended way of using pattern matching in the unified rule engine. And what is a sort of better way is to replace bind links, which are imperative links, which are just executed and give the result back. We can use them with declarative implication links. And instead of directly executing these bind links, we will have a sort of general rule which can be applicable to different implication links and combine them. And this looks really better from the AGI perspective. But actually, it might not be too efficient, especially in distributed settings. And another problem is that in this case, we implicitly assign some semantics to different kinds of links, which, I mean, this semantics is absent in Atomese language itself. So indeed, if we consider the code of how inheritance links or implication links are interpreted by pattern matcher, then we will find really nothing specific about them, and all the differences come from the rules which are defined not even inside the unified rule engine, but as rules for this unified rule engine. I mean, it's a sort of a program in the unified rule engine. So why we have built-in types of links in Atomspace, in Atomese, which semantics is defined in an external program written in a sort of some higher level built on top of this language. It's a sort of inconsistency and another problem with efficient execution of this queries within reasoning may be even more serious, at least from the practical point of view. So indeed, there is, as I mentioned, pattern matching is quite smart it's not just a static pattern matcher, it's something much more complex. It has a sort of crisp logic implemented in itself. So it knows AND links, OR links, greater than links, and so on. And semantics of these links is actually redefined in PLN, so in rule sets for the unified rule engine. So the question is, where does the reasoning start, and how do we know what semantics of this basic atom types implemented in the core Atomese language? And another problem is that interpretation of Atomese expressions can be actually too heavy, both as a basic reasoning step and memory retrieval operation. So if we consider, say, episodic memory design as or distributed atom spaces, then we would not like to make queries, execute queries to these huge atom spaces or graph, hypergraph DBs, which will take too long. We will like to have a sort of guaranteed time. It's really interesting that pattern matcher can actually interpret Atomese expressions. It executes grounded predicate and schema nodes. It executes built-in atom types like greater than links and so on. So it's quite powerful, but it doesn't always correspond to the ways of how we would like to use it. And if we consider reasoning, then it also can be quite problematic to use calls to the current pattern matcher as basic reasoning steps, because they can take a lot of time, because well, pattern matcher is solving subgraph isomorphism problem, which is NP complete, and this is another piece of the puzzle. So we have different simplistic use cases in which it appeared that the current design may be not optimal, or maybe not enough. And of course, as I mentioned, we can incrementally try improving things. But I'm trying to show that all these issues are actually interconnected. And here is one of such simple examples. Say we want to perform a sort of symbolic differentiation. So we have some rules that derivative of sum can be computed by this formula and so on. And we can write down such domain-specific bind link. It looks okay, but it actually doesn't work. For a number of reasons. We can apply it once and we will get the result, but we cannot apply it to sub-expression because instead of replacing the subgraph with the result, we will just get a brand new subgraph. Actually, there are some newly introduced types of queries to pattern matching which solve this problem, but there will be other problems like how to chain these substitutions in a necessary way. We can apply the unified rule engine, of course, and it will work also, although it might seem not too natural, like something like this. So we say that actually gradient of plus of some variables and so on is reducible to this expression if there are other expressions which are presented in our knowledge base. There are still some issues to this solution, but it can work in principle. Actually, if we think that this is not too natural, let's consider how this sort of things can be implemented in functional programming language like Haskell or something like that. So we actually, besides specifying some types, we write down an function. We call it, say, reduce, and say that if we apply it to this construction, then we will get this, and this will be just a recursive function. And actually, what we can see from this, we can see that deterministic chains of pattern matching turn out to be functional programs. And well, we also can ask, do we really want Atomese interpreter to be inside pattern matcher instead of be built on top of it? So we see that in functional programming, we also have something called pattern matching, and this coincidence is not random. And actually, we can imagine that, yeah, we can write down something similar in Atomese, and it will be the same, nearly the same pattern matching with some differences we will mention a little bit later. So actually, functional programs are built on top of this pattern matching. Why our pattern matching incorporates interpreter and not vice versa? And indeed, if we consider this functional language structure, and if we consider this binding for the unified rule engine, they're actually absolutely the same. The only difference is the order. So we have here the result, and which is here in the unified rule engine rule. And quite opposite, we have these two recursive applications in premises. And this is also not just a coincidence, because as Ben mentioned, there is a Curry-Horvath isomorphism, although it is typically applied to types, not to such correspondences. So actually, what I want to say is that the unified rule engine can be reduced to functional programming, although in a sort of inconvenient way. But what's important in the case of when pattern matching retrieves only one result. So we have a deterministic chain of pattern matching calls. So we can see that we can actually incorporate the language interpreter into the unified rule engine, not two levels below, so not inside pattern matcher, but quite opposite on the top of it. Of course, functional programming doesn't have a lot of features which are necessary for AGI. and we will see this a little bit later. But what's more important is that it doesn't support extendable knowledge base and non-determinism. I mean classical functional programming, not something like COC or AGDA. Actually, there are interesting directions, different directions of research, which already see this coincidence. So there is constraint logic programming, which writes a sort of something very similar to functional programming style code, which can be interpreted in two ways. So if we consider, say, bubble sort in a functional program, and if we consider this same, not bubble sort, but how to say, maybe the same model in a declarative representation in constraint logic programming, then they will be very similar up to some maybe syntactic differences. So we can see this as also not just imperative code, but we can consider it as a declarative specification of what we would like to achieve. And we can, if it's equivalence, if it's not implications, then we can read it in two ways. And even it's not an equivalence, we can also consider both forward and backward readings of such rules. And for example, if we skip this two indices and use only one of them and take a backward reading of a sort procedure, then we will just get a generator of all shuffles of lists. So it's quite interesting. We really can apply logical style reasoning or unified rule engine, I'd say, style inference to both backward and forward reading of functional programs as declarative declarative knowledge. So we don't need for sure compile them into a deterministic chain of applications. We can have non-determinism, and we can have reasoning and so on to choose what branch of applications we would like to take. Why this correspondence is important is because of, in particular, functional probabilistic programming, because in functional probabilistic programming, we also write down some code in a functional language style, but we add some additional semantics to it, like sampling from different probability distributions and doing some conditional inference. So generative models are very important for machine learning, for AGI in general. And actually, probabilistic programming has some huge problems with efficient inference, which might be able to solve with backward propagation of constraints closer to the places where sampling takes place. So if we consider some simplified example of query in Church and similar query in Atomese, then we see that the structure of these queries is nearly the same. There are some differences like sampling from random variables and so on, but in fact, this bind link for pattern matcher is very similar to this rejection query in Church. There are different aspects which I'm not going to discuss in detail. What I'd like to notice is that actually basic sampling from random variables can be implemented in Atomese, and actually it has already been implemented with random streams and so on. So we can just put here a random stream and execute this bind link, and it will work exactly like rejection sampling. But the problem, there are some problems with this. Rejection sampling is too simplistic. We cannot easily implement, for example, MCMC or genetic programming over execution traces of probabilistic programs. So, I mean, probabilistic programming language interpreters are interesting because they go beyond this simplistic rejection sampling and introduce more efficient methods, at least like Monte Carlo Markov chains or Metropolis Hastings algorithms. And it is not easy to implement this in the current version, because in this case we will need to deeply modify pattern matcher itself, and it's kind of problematic. Also, even if we modify this pattern matcher in such a way that it will construct execution traces of queries it is interpreting, and apply MCMC steps to these execution traces and implement MCMC algorithm, it would be cool, but we still will not achieve the cognitive synergy, because what we would like is to apply backward chaining to analyze these expressions and propagate conditions back to the premises or random sampling places. So what we would like to do is to have both of these things in the same place. And this means that we should work most likely on the level of the unified rule engine. So once again, it seems that we need to implement Atomese interpreter not inside pattern matcher, but on the level of unified rule engine. So this is only one point regarding Atomese. I'd say this is sort of design choice how to deal with pattern matcher, Atomese, unified rule engine, PLN, and so on. So we indeed leaned towards using static pattern matching because it can give us efficient queries to the distributed atom space, and we will, in this case, not need separate distributed episodic memory with more simple querying procedures. This static pattern matching can be used as a basic operation in FPS style interpreters, including probabilistic program languages. It also can be extended for dependent type languages, although there can be some tricky things. And it also can be an atomic reasoning operation or cognitive cycle, which we can be sure will take not too much time. And on the other hand, we tend to think that the unified rule engine and Atomese interpreter should be pulled together. And in this case, PLN will be a sort of a library or DSL in Atomese. Well, I'm not sure if I have time to go into other details, but in any case, I would like to quickly, yeah, I guess I have some time. Okay, I would like to describe one of our experiments with the decomposed interpreter. So, as I mentioned, we would like to have an interpreter which is based on static pattern matching, and which will have some interesting features like the possibility to make reasoning, non-determinism, and so on, and the possibility to any time execution and maybe multi-target execution. So let's start from a simple example. In a functional language, we would like to say calculate a factorial function, and in sort of Atomese, it would look like something like this. It's a simplified syntax. And the first thing which we see is that if we would like to make use of these graphs with pattern matcher, then we will need to not just say, please calculate me fact 5, because pattern matcher will not know how to do this. So we will use this query, and it will find in knowledge base this one, and it will substitute 5 to x, and the result of substitution will be substituted here. So these two subgraphs are unifiable, and one thing which we see that it actually goes a little bit beyond what current pattern matcher is intended to do, because the typical use of the current pattern matcher is bind link, which doesn't support I guess variables in knowledge graph in this sense. So it supports variables in queries. So we could write bind and so on, but it will not substitute 5 to x. On the other hand, there is a dual link, which is not being used too often, and I'm not sure if its implementation really complete or not. But it's quite an interesting idea, because this dual link does something opposite to what bind link does. It searches for patterns in the knowledge base which can be matched to the query. So instead of taking a pattern as input in as query and find its groundings or groundings of its variables in knowledge base, it does the opposite thing. But what we really need is to combine these two types of links in one matching procedure, and it's not extremely important, but that's another thing which differs, which makes the difference between possible Atomese hyperon and say Neo4j, which also doesn't support variables in knowledge base. So we can see that we can naturally use such extended pattern matching, pure static pattern matching as a small step of interpretation. What we would like to point out is that the result of this match should be further processed by the interpreter. So we would not like the pattern matcher to do recursive substitution of fact in this expression and so on, because it can be actually non-terminating and so on. But we would like to do just one step of interpretation, and pattern matching, static pattern matching can do it well. So yeah, that's what I already said. The next thing is that if we break down our interpretation process in such steps, we can actually easily do this in parallel for different targets. And say we have fact 5 as one target and fact 2 as another target, and we have a stack or list of or whatever of these targets, and we as in parallel or consequently apply our pattern matcher to one target, get the result, put it at the end of the list of these targets, and go to the next target, and so on. So we can either emulate parallel achievement of these targets or do it really in parallel, and so on. The important thing that it will be non-blocking. So like in OpenPsy, we can have different rules as goals. Here we can have different targets which we would like to achieve or compute. And actually, these targets can be even grounded in external world. So one target can be an interpretation of images of frames which are coming consequently, and another target could be some real goal like find and drink water or whatever, and it's easy to implement this kind of concurrent anytime and non-blocking processing of these targets in this sort of interpreter. And if we consider this not just a functional programming stuff or evaluation of functions in a sort of imperative way, but if we add non-determinism to this and possibility to do reasoning, then it will be actually what we are lacking right now. So we can change our atom space during the reasoning process, or evaluation of one target may change some stuff in atom space which will influence the evolution of another target. And this is actually a sort of problem in embedded agents or embodied agent applications. For example, in the case of smart home, we can have the target for turning lights on. And we can start reasoning how to do this. Like we know that this lamp is connected to this power switch, and we can control it. So let's send the command and then check if the lamp has changed its status and so on. But if during, well, maybe it's not a very good example because this reasoning is quite simple and has just a few steps. But in any case, if during this reasoning process something has changed in the real world and we've got that user has already switched the lamp on and we see that the goal is achieved, then we will not need to continue this reasoning process. The goal is already achieved, so everything is okay. So if we are talking about such embodied agents or applications, then this real-time reasoning would be really cool, and this is what the unified tool engine is not really applicable or convenient for. So I think that this is maybe right way to go, to take these small steps which we can consider as non-blocking and build this multi-target reasoning or Atomese interpretation on top of it. And actually, if we are talking about this list of targets, then we can ask where are they located, and well, they are located in the atom space. So actually, we can change the order of them. We have one target which takes another target and put it out of the list or whatever. So we will have the possibility to formulate new targets for interpretation or reasoning by means of Atomese programs themselves. So it's a sort of maybe conscious, not a good word, but something like conscious control of attention. So like I would like to focus on this presentation, so I'm trying to consciously put this target in my stack of targets for being achieved or evaluated, and I consciously reduce the priority of other tasks. But in any case, if someone goes in the room and hits me, then for sure my focus will be changed, and it's not too difficult to emulate in this style of decomposed interpretation or reasoning. And we have this as a very simplistic prototype, very preliminary, but it's just a proof of concept which shows that it can really work. Okay, I guess I already said about reasoning. Basically, yeah, it's not about just functional programming, but it's about reasoning. So we can represent PLN style reasoning in such a way. There are some issues to this, like how to process with truth values and so on. And values is a very interesting question, which unfortunately will not be covered in my current talk. It was very interesting to hear Linus' ideas on declarative manipulation with values, and it's somewhat close to what we are also thinking about. Okay, so maybe I will skip this one. Well, the one thing I would like nevertheless point out that pattern match query language is kind of different, so we should not mix it with Atomese. It's like high-level syntax of Haskell, so it's not here. Let's say for example, something like this. So we have a very specific syntax to form pattern matcher queries, which are processed, well, not by the compiled program, but on the level of matching this syntax, these patterns statically and syntactically. So if we consider the current pattern matcher and current Atomese, then we will see that such links as end link are very overloaded because they are used in pattern matcher, they are used in unified legend or PLN, and they are used in different ways. And we just need to understand that these are very different things, and they are situated, placed on very different levels of our multi-layered system. Okay, so besides the question of the interpretation and pattern matching process, there are some other important things we are discussing now, like atom types as first-class objects. It's quite important from the usability point of view, because for example, if we want to introduce some simple new atom types like gene or molecule nodes as in Atomspace, then we need to add them to the script, compile, install, find out that we forgot about the bindings in Python, and we are working in Python. We will need to do some additional things, and only after this we will be able to use, say, gene node in Python. But well, if we consider Haskell as example, we can just say, hey, let's in our code, not in C++, not in some external scripts, we will just say, hey, we have this data type, and we can use it immediately. So it's much more usable, and it's what we would like to be able to do. So to define atom types in Atomese itself, and it also, yeah, there is some confusion about the role and semantics of atom types in Atomese. For example, in case of virtual assistant, we would like to have a sort of restaurant node. But in this case, well, should we have a restaurant node or just write down inheritance concept, say chili pizza concept restaurant? So what should we use? Which one is correct or not? As I mentioned, we don't have the semantics of inheritance links built in Atomese. So it's not clear if one or another approach is better, or is it just a syntactic sugar to this one? If so, then well, maybe this more verbose approach is better, because actually it allows us to do pattern matching on sort of types, because we cannot specify an unknown type and match against not type. So this sort of things are a little bit confusing. We would like to be able to also specify signatures for built-in link types. For example, I don't know, it's because it's hidden somewhere in the code. Maybe it is implemented, maybe not. I can check it experimentally or dig down into the code. But does evaluation link expects only predicate node as its first argument or not? It's very difficult for a user to know, because there are many things that are assumed, you should do this in such a way, but actually they are not in the code. They can be on the level of PLN rules. And if I'm not using PLN, should I assume such semantics of implication or evaluation link or another semantics? And if we have such signatures, then there will be much less confusion, and the user will just see that, yeah, maybe not C, but she will get static type checking error if when trying to use non-appropriate node type as argument to evaluation link or something like this. Yes, and of course, if we have some functions, rules, and so on, we would like to be able to do type checking. There are some tools being introduced into the current version, and that's good that all these positive changes are taking place. But maybe we still need some more systematic and overall solution to this. Yeah, and about matching against types, I have already mentioned. Okay, and this is actually quite relevant for sort of AGI theory as well, because types is one of possibilities to combine functional and logical approaches. I mentioned before a little bit different approach when we just consider statements in a functional language as declarative statements and reason about them, and it's actually something that is already implemented in the unified rule engine in terms of we specify declarative rules and declarative knowledge and rules for reason about them, and that's really cool and inspiring. But another way to do this is to introduce some type calculus, because as one of the basic examples of Curry-Horvath's isomorphism is that the code can be a proof to a theorem which is defined in terms of relations between types. So if we can construct a program which will be type checked, then the type is inhabitant, and we have proven the theorem. And if we go from basic types, algebraic, generalized algebraic types, and go to dependent types, then we put more and more to this logical part. So we start to be able to reason more and more in more detail about programs themselves. And this is one of ways to combine these different paradigms. Yeah, okay, and there are, of course, connections to other theories like category theory, which also gives us very interesting insights on how languages can be designed. For example, I would like to mention just one concept from category theory. So we can have data type, and we can define something over this data type. So it might look as a ordinary function, but it is not. What is it? It's actually a sort of a declarative definition of what Fibonacci numbers are. And this declarative definition is actually an algebra over an end-of-functor net F. And catamorphism over this algebra calculates Fibonacci numbers. So it's quite interesting that instead of defining a recursive function, we can just define an algebra in declarative way, and there is a common mapping from these algebras to the process of their interpretation. And actually, it's a very simplistic example, but in the very similar way, we can just define interpreters as of domain-specific languages as algebras. And instead of the basic implementation of catamorphism, which is just a very simple recursive function, we can do something more interesting. So we can modify this core process of recursive interpretation of expressions with some reasoning over declaratively defined algebras, and we will have a way to reason over languages themselves. And this is quite interesting because we can decompose this definition of language from the process of its interpretation, and we can try different inference methods. So we decompose them, and but these are quite preliminary thoughts. There are many other interesting things from category theory, which some of them Ben has already mentioned. There are there are, for example, category theoretic knowledge representations which have some interesting properties, and it's quite interesting to construct a sort of formal model of our knowledge representation in certain sense. Here is one very simple use case example of how can we make how can we benefit from it. For example, we have say inheritance link, and we can define a link root which will be defined as a sort of pattern. So if we have an inheritance link from X to Y, then we sort of call root Y, and if there is no such thing, then X is the result of evaluation of this link. So in this case, we will mix these types, these algebras and so on. So we can just use catamorphism over this type definition to get root nodes in our hierarchical ontologies or something like this. It cannot be done in current Atomese, but it can easily be done. Possibly easily can be done in the design we are thinking about, and if we succeed that, then it will be quite a convenient tool to do different such things like analyzing knowledge graphs in different ways. It will be much easier to define say a pattern miner in Atomese itself, and so on. As I mentioned, well, we hope to solve some problems of probabilistic programming if we successfully combine these things. For example, this very simple probabilistic, say, model rejection query over 40 flips of a coin, which are required to all be true. It will be executed for many hours. But using logical reasoning, if we consider it in a similar way, by the logic style reasoning, by backward chaining, we can easily conclude that all x are true, so there is only one possible solution to this problem. And this sort of examples are exactly why functional probabilistic programming doesn't work as a solution to AGI. Although it looks very natural to make machine learning, reasoning, knowledge representation in probabilistic programming, but it always starts with random sampling and some tricky methods don't help to overcome this kind of problems because they always go in one direction in a computational style way instead of using sort of reasoning and so on. Yeah, and as well, maybe Ben didn't mention this. He has some ideas on category theoretic solutions to symbol grounding problems and so on. So category theory and type theory and so on are very interesting, both from a AGI perspective and from the Atomese language design perspective. And this is the place where exactly they meet each other. One last thing I'd like very quickly to go through is that when we start thinking about formal semantics of Atomese, then we immediately end up with the question, what is atom space? So shouldn't atom space be a well-defined component of Atomese? For example, if we go back to this decomposed interpreter and recall that targets are placed in Atomese, maybe in atom space, maybe in the same atom space as knowledge base or in the different atom space, because we can have many of them. Then we should be able to address atom spaces from Atomese itself. And this is also one of the things being discussed with respect to the current OpenCog implementation. But we can solve it, maybe hopefully solve it in a more fancy way if we do everything from scratch. So, well, what is atom space? And if we try to define it formally, then it's just a container, and containers are functors in category theory, in category theoretic interpretation of functional programming languages. It should be a grounded functor because, well, it can refer itself. So we cannot constructively define an atom space which contains the program which contains the references to this very atom space. So we can define it just as a grounded symbol, and well, grounded predicates, schemas, objects, and other symbols is a very yet another very important topic for the discussion, which I don't have time to do now. but in any case, it's a grounded functor. We can generalize it and say that it's a type class with a certain interface. And then we can say that within this type class, there can be possible different instances of it. So we will have natural transformations between different atom spaces or their implementations. And we will actually be free to choose different implementations, different even different functors, because we can represent an atom space as a plain list, because when you are writing down Atomese programs now, you're actually writing down a set of expressions in plain linear order. So it's just a list, and while it is being added to the real atom space container, it's just a natural transformation from the text representation or text functor to this hypergraph functor. So actually we can have a quite cool automatic mapping between them, and we have experiments, some experiments with this. And we can actually say that, well, we may not have one very best implementation of our hypergraph container, because for one type of tasks, one container will be better. For other type of tasks, another container will be better. To store charges for reasoning, we can use one type of container, and for storing knowledge base, we can use another type of container, and they can be sort of natural transformations. So even natural is isomorphism between them, and so on. So we can just resync all this. So this gives us some freedom how to approach the design of Atomese Hyperon, because we don't need to make some hard decision choices at the very beginning. The idea to provide a sort of maybe APIs, formal model for atom space and Atomese, which will be possible to implement in different ways. Of course, it will not solve the problem of AGI in general, and that's exactly why we would like to construct Atomese Hyperon as a platform for possible implementation of different inferences, inference strategies, different semantics, like different type systems, different logic systems. This is partially already done in the current version of OpenCog, because well, unified rule engine allows you to define different rules which assign different semantics or interpretation to different types of links. You can say use something like fuzzy logic or crisp logic or something else, but there are problems. What is missing right now, heavily missing, is the possibility to represent inferences themselves, to reason about inferences. There is an ongoing work on meta inference, meta reasoning in OpenCog, and it's really cool, but it seems like we are missing this framework in which it would be really convenient to do such a sort of R&D. And of course, when we go further, we would like to have an efficient inference to different domains, which can be formed by sort of meta learning. During the AGI 20 virtual conference, there was a panel in which I participated and discussed a little bit. I don't have time right now to go in detail, but the basic idea is that it's not possible to have one inference strategy which will be efficient and general and applicable to everything. It's quite obvious, although the details of this are tricky. And one of possible ways to consider what AGI is doing or should be doing is the specialization of this general inference procedure to different domains. And yeah, in order to do this, we should be able to represent different inference strategies as also sort of first-class objects, or just in a declarative way, in order to be able to combine them, to reason about them, to apply inference to this inference itself, and so on. And well, this problem is not solved yet, so we are not sure how precisely to approach to the design of Atomese language, but we at least have some ideas, both from category theory and from other existing frameworks. Okay, so maybe I should stop here. Basically, we have some possible design decisions, like extracting or separating static pattern matching from dynamic pattern matching from Atomese interpretation, and merging bind link and dual link into unified queries, and to combine reasoning with Atomese interpretation, because it's actually nearly the same thing, and we should not duplicate entities. But there are, of course, many more questions to discuss. So thank you for your attention.
Thank you, Alexey, for that very illuminating and in-depth discussion on Atomese. And as you pointed out near the end, it's really hard to disentangle Atomese completely from the atom space. They're really integrated and a lot of the questions come up either, talk about the overall architecture, or very specific questions within specific topics, problems you discussed within Atomese. But there is one question I'd like to ask that I think is most germane to the discussion of Atomese 2, which is, if you implement types for atoms, that means you are mixing your knowledge scope with the structure behind. What are the limits of that combination?
Well, that's an interesting question, because if we take different type systems, especially dependent type systems, if we go too far, they become undecidable. So we cannot infer everything about programs. Yes, and that's why we have a number of options what to do with this. As we implement the most powerful but efficiently decidable type system, like linear types or something like that, as Ben mentioned, or we just move the burden on this reasoning to the cognitive architecture itself. So it will acquire more and more knowledge what to do with types, what it can infer, and actually maybe we can somehow combine this. So we can start from some built-in type inference system which will do a lot of useful work, but we still will be quite flexible, say by using gradual typing and so on. So we can do this on the level of Atomese or Unified Rule Engine programs themselves, but I guess maybe Ben can answer better to this question.
You know, there's a lot to say, but I think we should
Move on.
I don't think I have a concise answer, so I think we should move that to the panel and continue with the event. Otherwise, we're never going to get there.
Yeah, they're right. Actually, there was another question regarding distributed atom space, and rather than ask it here, I don't know, Cassio, Cassio Pennachin's going to talk next, basically about steps towards the distributed atoms.
Cassio actually was the chief architect of the original OpenCog version, and hasn't been as actively involved in OpenCog constantly as a few others, but has kept his hand in. And I've been working with Cassio ongoingly since 1998 on a series of different AI projects, and we still mostly tolerate each other reasonably well. And I think I mean, Cassio would have a lot to say about what Alexey has just gone over and every aspect of OpenCog implementation and AGI, but what he's going to talk about now is the distributed systems aspect, which is a whole other world unto itself, yet one that has to interoperate closely with all the programming language particularities that Alexey has just reviewed. So yeah, take it away, Cassio.
All right, thanks. Let me do some screen sharing here. So let's talk about what it would take to make our atom space a distributed, scalable, and persistent store for OpenCog metagraphs. And distributed because, in spite of advances in computing power, we managed to make our algorithms even more hungry as time goes by. So we still need many machines to build an AGI. Scalable because we need to do that in a way that's reasonably performant. And persistent because AIs need to have long-term memories. Now, like I just said, we need to work with very large knowledge bases, and the current atom space does a decent job of working with the knowledge base that can fit within a single machine's RAM. Also, this current atom space does not let us do everything we need in terms of our optimal configurations. And if you think about a proto-AGI or AGI deployment across many machines, you're going to have some machines that are primarily dedicated to, say, perceptual processing of video and auditory inputs. And you have some machines that are primarily storages of long-term memories or dedicated to deep focused inference. And these machines will place very different computational profiles as requirements for the atom spaces supporting those machines. Now, well, we need a distributed system that supports all of that, and we need to write our own because the graphs we're talking about are peculiar. They're metagraphs, and we'll get into that a little bit, but the peculiarities of the graphs we need to support and the peculiarities of the processing you want to do on top of those graphs means regular graph databases are a bad fit. And yes, we've looked at that. We actually even implemented Atomspace on top of Neo4j once, and it was exceedingly slow and cumbersome. And the main reason for that is that we're not talking about your regular vanilla graph database. Metagraphs have some properties that they share with your typical graph database, have nodes and links that are strongly typed. And they have properties that can be attached to those nodes and links, the key ones being the truth values and attention values, which tell you how important each node or link is. But they also have higher order links, which are links that point to other links. And well, people who are watching Alexey's Atomese talk saw a very large number of examples there. And they have links that can have a very large number of targets. Now, all of that could be represented as graphs. And then there is a straightforward computations that do that, but they come with a significant performance penalty. And that still means you're storing your data and you're caching your data and you're fetching your data in a format that's very different from the format it's ultimately getting used. It's already hard enough to get this Atomspace to perform well without having to do knowledge storage transformations all the time. Additionally, for Atomese reasons, a number of those nodes and links are executable. They can be functional nodes and links, and they can embody graph transformation rules, including variables that have to be filled in. So you have to have a database that's able to store its own representation language, and it's able to affect the contents of the storage by executing what's in there. And that's something, again, that is possible by building a layer on top of a graph database, but it's definitely not natural. Finally, in practice, and this is relevant for tuning purposes, an OpenCog metagraph is often a gigantic collection of smaller acyclic graphs, tree-like structures with some repetition in the nodes that show here and there, which means you can do things like deduplication, and it means you can, if you can identify those subgraphs, you can use them as your unit for key decision making, like which subgraphs get to be in RAM at any given time versus persisted to disk, and which subgraphs should be replicated across the entire cluster or only be present in a subset of the machines in the cluster or in a single machine. Now, putting all of those reasons together, you have the case for why you want to do our own database. And what does that look like? Very quickly, for the benefit of those who haven't been paying attention to all the talks since yesterday or not familiar with OpenCog, the Atomspace is a knowledge store for atoms, and we call both nodes and links atoms in OpenCog lingo. And nodes have names and links have immutable collections of targets. Atoms can be realized, which means they are in RAM. They could have multiple copies. Those copies don't have to be consistent all the time. They could be serialized. Atoms that are important enough get to be serialized to disk and can be fetched later. Every atom has a unique identifier across the entire system. And some atoms can have their own importance and truth values, as well as other values that can be attached to an atom. Some atoms just get default values for truth. Some atoms never get an importance value attached because they're created and removed too quickly. These values are the mutable part of an atom. Types, target sets, node names are immutable, but a lot of what the OpenCog does on top of atom sets is changing their truth values. And what OpenCog's attention allocation is all about is changing their attention or importance values. These values will be changed at the same time in different machines once you have a scalable distributed system. They will create inconsistency. And we can live with that for a while, and we'll talk a little bit about how we address that. final constant that's key here is chunk, which is a set of connected atoms that has some meaning for processing. That's an example of those directed acyclic graphs. Sometimes a chunk is an executable piece that's an evaluation of a given procedure or execution of a given schema. Sometimes it's a set of interconnected atoms representing a knowledge datum. Now, chunks are important because atoms are tiny. Most links have a small number of targets. Most nodes have nothing of particular interest attached to them other than a name that's usually compact, a truth and attention value that's usually a few floating points each. Atom creation and removal happens all the time. New atoms are created very frequently as data comes into the system, or as we do inference, or as we do pattern mining. All of those processes are going to generate a very large number of atoms. Most of those atoms are important only in the moment and do not have to be kept around, so they can be removed very frequently. Some atoms are extremely important, and this OpenCog recognizes that by attaching a high long-term importance value to them, and those atoms will live a very long time, which means the lifetime of an atom is highly variable. Now, atoms are tiny, and their creation and deletion happens all the time. Chunks can be small, medium, or large. A chunk can be a dozen atoms. A chunk can be a few hundred atoms. And it's very rare that when working with the atom space, to look at the world as you perceive it, decide an action if you're controlling a robot, or annotate a model if you're doing bioatom space, medicine-oriented work, you are almost always going to look at chunks. You're almost always going to look at a graph that has a bunch of related atoms, and you don't usually make decisions about a single atom without involving everything in its vicinity, which means that the design decisions for the distributed atom space have to be made about chunks, not about individual atoms. Having set the stage, what do we want from the distributed atom space? Well, the obvious one is we're designing a new database, but we're designing a database to be AGI-oriented and OpenCog-oriented primarily. So we're designing this to support the metagraphs that OpenCog depends on, and to support efficient Atomese implementations on top of it. AGI requires massive knowledge stores. This database has to be scalable. And at the same time, AGI has heterogeneous computing power requirements and heterogeneous data usage requirements. So perception subgraphs are created very rapidly and removed very rapidly. Long-term memory is slowly consolidated and hopefully kept for the long term. And if it has to be kept for the long term, then it has to be persistent. But only a subset of the hypergraph has to be persistent. Only the chunks that have proven themselves to be valuable and have, as a consequence, received credit and have their importance values boosted get to be persisted. Everything else can go away if a process dies or the computer is rebooted. And important knowledge will be reconciled by the distributed atom space. That means we're looking at eventually consistent behavior, and we're only applying that to the subset of atoms that are important enough to the system to merit going through the reconciliation process. Again, we're talking about systems with billions of atoms. We're talking about moving them all over a computing cluster. If we keep every single atom consistent, there will be no computing power left to do any of the AI. So our goal is to build a system that can handle eventual consistency of a smaller subset of your entire atom space. And that subset is going to get reconciled as quickly as its importance warrants. So machines will have different profiles. That means local caches have to be flexible. Each machine will have a bunch of AI processes running on it and will have a local cache of a subset of the in-RAM distributed atom space. What goes into the local cache, how often it gets reconciled with the rest of the system, and what gets flushed out at what rate depends on the goals for that machine. Chunks of atoms can live in a local machine. If they're important enough, they can be cloned to different machines. If they're really, really important, they may be there in nearly every machine. In some cases, you want to mark a chunk local only. One example for that is maybe you're doing some program learning with Moses, and while you're learning a large program population, you don't need to send your candidates elsewhere, even though you're running a distributed Moses run. Most of those chunks representing modules remain forever in a single machine, and the important ones are the good solutions that are shared across machines in the learning cluster. So a distribution policy has to be pluggable, and that policy tells us which chunks get to live in which machines. And we anticipate that a proto-AGI or AGI deployment of OpenCog will have machines with a wide variety of different policies, and the Atomspace has to be flexible to handle all of that. Distributed query processing is basically pattern matching, which is looking at a chunk template with variables, finding a chunk that lets you realize all those variables, and depending on the pattern, run the graph transformations on top of that. So that means we're talking about an atom space, but we're primarily processing far larger chunks of atoms, and we're primarily doing that through a pattern matcher interface that looks either at the full atom space in RAM and disk, or at the full atom space in RAM, or at the local atom space. And it can also be further restricted based on truth values, importance levels, atom ages, and it can be made to run only locally if necessary, which is sometimes necessary for performance reasons. But this is what we want to build, and of course, we're not anywhere near having code to show and benchmarks or anything. We just have some very preliminary thoughts on how we're going to build that. Now, the first key design decision, which is somewhat related to some of the thoughts Alexey was saying before about maybe there's multiple Atomese interpreters and multiple versions of Atomspace, and you can reason about them if you're grounded in knowledge. So Atomspace and the AtomDB are two separate entities. They are going to be built with different philosophies. The Atomspace is primarily about processing. And when I talk about processing, I mean it's going to offer a rich set of APIs for OpenCog applications and AI algorithms to be built on top of it. This is where the typology of atoms gets defined, and different applications will have different sets of nodes and link types. A bio application will have a very different set of node and link types than a customer support conversational agent application or an embedded robot or something like that. Since the Atomspace is primarily about processing, this is where pattern matching, pattern indexing of chunks takes place. And this is where the building blocks required for Atomese interpreters to be built are provided. The AtomDB is about storage. And in a single machine version of the Atomspace that currently exists, you do have a high-level API at the Atomspace level that includes a pattern matcher, used to include the unified rule engine that got removed into its own repo recently, and includes APIs for manipulating truth and attention values, and includes some policies for pattern matching and things like that. But we relies on the atom table as the storage for all those atoms. So now we have the AtomDB as the distributed storage system. And the AtomDB is a combination of a distributed cache with configurable caching policies. It's a place where replication policies are implemented. It's the AtomDB that determines which atoms get sent to which machines and how, and users can plug different policies there based on their needs. It's where atom consistency is implemented according to whatever parameters are chosen by the users. And it's where persistence is implemented, possibly with multiple options. So what does this look like? At the top layer, you have a bunch of different algorithms, PLN and Moses and OpenSci and ECAN, interfacing with the local version of an Atomspace. And the local version of Atomspace is RAM only, and the atoms are actually kept in the local cache that's part of the AtomDB. The AtomDB has a local cache in each machine, and those all put together basically are the distributed cache, which is RAM all over the cluster, and there's a persistent storage layer, which is disk. And this lets you have a wide variety of machine configurations. You can have machines allocated to different kinds of cognitive processes, and you probably have some system-level machines. You could, in a large cluster, have a small subset of those machines that do only atom and chunk reconciliation to improve the timeliness of eventual consistency and let the other machines get away with doing whatever their AI processing is that breaks that consistency again, and the loop repeats. The AtomDB provides a very streamlined, low-level API for handling atoms. It's your basic add, delete, update, and query the local machine interface. So, a CRUD system. And a distributed API to deal with chunks, which lets you fetch chunks to the local machine, sync chunks back across the distributed system, which proposes them for reconciliation, and the reconciliation policies determine when and how they're going to get reconciled, and release chunks from the local machine. We don't need these anymore. It has a distributed caching layer, and we're looking at using Apache Ignite for that, but well, this is still very preliminary. And ultimately, it backs into a key value storage system. We're looking at using Badger and RocksDB as options for implementing that. Now, since the AtomDB is the component that does consistency, it's interesting to talk about that and a little bit. And consistency is implemented by, first, there's a mechanism, which is the AtomDB API lets you send a sync request for consistency and lets that request be processed according to whatever policy is implemented. But there is a distributed cache layer that sends those chunks around to consistency implementation providers. So each machine has local queues of atoms that have to be reconciled. The priority of reconciliation versus other operations is pluggable. You could say, I'm going to spend this fraction of my computational cores on reconciliation. That could be 0, in which case the local queue just gets sent around elsewhere. It could be 100%, in which case you do nothing else. And for some machines, it could be like 10% should be enough for a lot of the highly important atoms to remain in a consistent stage. And policy is how each atom space is going to make use of that mechanism. And that's an AI decision. It's about which chunks to send for reconciliation, which can be done with, say, setting importance thresholds. So once a bunch of atoms in a tightly connected subgraph has high enough short-term or long-term importance on average, then it gets sent for reconciliation. And you repeat that reconciliation check every now and then, just in case. Those queues can then be priority queues based on a function of importance. The other thing you want to do is have thresholds based on how much the truth value of an atom is changing, depending on what it is you're doing to it and what kind of inference you're running. You may come to new, highly confident conclusions that change a lot of what you thought was the truth value of a given chunk of atoms. And in that case, even if they're not particularly important, that's a large delta in knowledge, and that makes it more urgent to reconcile those atoms. So policy is basically a pluggable implementation that considers atom importance, the ratio of change to truth values, and how much resources to allocate for consistency versus doing other algorithms, which is essentially breaking consistency. That's what we have so far. It's pretty early stages for the Atomspace design and architecture process. So basically we have a large set of goals, some key design decisions, and we have some prototyping code that's hopefully going to evolve and be released soon. I made this a little bit quicker because we're running late, and I'd like to have time for questions. So, questions?
So, yeah, so there are a few questions. And thank you for that very clear and succinct presentation. So the first one, I think this actually came up in the discussion yesterday. I was just trying to think about this. It's actually two questions in one here and I think that, and I'm trying to remember where it came up in discussion yesterday, but do you really need to load each individual database to the atom space, like data on all genes, diseases, et cetera? Why not to approach the problem more like a human, i.e. refer to individual records of external databases each time it is needed?
I would argue that's not how humans process heterogeneous information, right? In the first place, yes, you're going to fetch, a human is going to fetch information from various sources if they need to think and come to some conclusion about that data. The way you process that is by having everything in your brain and making connections to other stuff already in your mind, other memories you have and other useful knowledge you have. Right? I mean, you could, for instance, just build a querying interface to gene ontology, and then you want to do annotation of a given biomedical classification model, you query the gene ontology on the fly. But the point of having everything in the atom space, and one of the reasons you want the atom space to scale, is you also want to store knowledge about which gene ontology categories are useful for that date, for that model, and you want to be able to relate that information to what disease the model was looking at, or what kind of data is it? Is it clinical data? Is it gene expression data? What sort of biological processes are being studied, and so on and so forth. And if you want to run inferences that lead to suggestions for drug discovery or personalized medicine, you want to have a trail of past inferences that are useful for a similar domain. And you want to connect that trail to the subset of the gene ontology you're looking at right now. So if you want to not store a version of gene ontology in your atom space, you have to do that connection process every time, because you don't have those nodes and links. Whereas if you do have those nodes and links, then you can learn about the relations between gene ontology nodes and links and the features of that model and other biological databases like drug databases and protein-protein interaction databases. And you can learn about what kinds of inference rules and inference patterns are useful for this kind of data. And that depends on the data set you're looking at, and so on and so forth. So you lose all that subtlety.
Okay. So a couple quick, hopefully quick ones here. How to protect the atom space against DDoS attacks? Is it because flushing atoms requires AGI tokens?
That's a misconception, right? There is nothing that requires payment. There's
I think, okay, so I guess the main question is how to protect it against denial of service, right? Attacks.
Well, the same way you would protect any database system that runs a bunch of servers, right? I mean, Atomspace security is the same kind of security that's needed for a distributed Postgres deployment or a Cassandra deployment. It has no peculiarities that would make whatever best practices are used there, and I don't claim to be an expert in those, any more or less effective.
And more to the point, so getting to the reconciliation operations, the question is, what scale is that done at? Is it global, or can a chunk atom be replicated on all distributed nodes? Is reconciliation done at the level of a chunk? Can it be done at the level of an atom? Can it be done at all of those, say? Or
it will never scale if it's done at the level of an atom. It has to be done at the level of a chunk. Can a chunk be replicated on all distributed nodes? If it's important enough, yes. Or if a user configuration says these chunks have to be in every node, no matter how important they are, then that happens. Otherwise, they're replicated as needed based on their importance. And their importance can be context dependent, right?
okay, so I think that's all the questions that we have for now. So I think we can probably transition and go to Nil. And it was originally Nil and Kasim. Of course, Kasim, the Ethiopian internet's having issues. So Nil's going to be talking on his own on Moses, and in particular Atomspace Moses, which is a transition of Moses. Moses is meta, so evolutionary learning, meta optimizing semantic evolutionary search. And I'll let Nil take it away. Nil, are you muted?
Can you hear me?
Yes.
Okay, can you see me now?
Yes.
All right. Okay, so what do you see? Do you see a presentation about Moses ported to the atom space?
Yes.
We do. We see the very beginning of the presentation.
Okay, great. So, well, my presentation is fairly small, but I'm hoping to give you some small demo in the end. So, as you understood, Kasim was supposed to do the presentation, but due to more or less technical reasons, he couldn't.
Technical reasons like the internet being shut down in the entire country of Ethiopia. Yeah. Yeah, which is
a pop star.
Yeah, it is, and the possible outbreak of a civil war or something. I think Ethiopia is back online now, but not the internet's not good enough yet, letting like live video presentations be feasible. But yeah, Kasim, who's in our Ethiopia AI office working with SingularityNET and OpenCog has done a lot of the development on Atomspace Moses. So it would have been cool to have our Ethiopian contingent actually in OpenCogCon giving the talk, but no internet is a major obstacle, and Nil has been sort of the guru behind the project all along. So he's perfectly appropriate to do the presentation also. And we introduced Nil last time, I guess. He's been at this like 10 plus years, including a lot of practical work with the existing version of Moses, which is sort of part of OpenCog conceptually and culturally, but Moses has been like it's a separate C++ code base doing probabilistic genetic programming for automated program learning, and we can run it separately, then import the programs learned by Moses into Atomspace. And so this initiative Nil's going to talk about has been about how to get rid of that division between the Moses probabilistic program learning code base and OpenCog Atomspace, and just do Moses inside Atomspace, which would have all sorts of advantages for making the algorithms stronger and more general and more powerful. Also can have performance disadvantages in some aspects, which may go away with the shift to OpenCog Hyperon. So yeah, I'll continue now.
Yeah, so as you understood, Moses is a program learner. Moses stands for Meta Optimizing Semantic Evolutionary Search. So let's break down that. So meta optimizing, well, it's because the optimization itself, the search of a solution, is also optimizing. So the search itself is improving as the search is taking place. Well, actually, that was certainly in the initial design of Moses. Today is a little bit more subtle than that. I mean, Moses used to basically use a Bayesian network to model the fitness landscape, and it worked. But I mean, it wasn't perfect, and turns out that doing some more systematic hardwire ways worked just as well. So it was progressively replaced by a version of the stochastic local search plus some crossover. But the foundation are there to basically go back to the roots and spirit of the meta optimization, and I'll say a few things about that. Okay, what about semantic? So there are several things. First of all, the semantics of the program that we are looking for is taken into account. The semantics in the sense of the mapping between inputs and outputs, and this is used to basically maximize the diversity of the population we're looking for. And there's another level of this of how semantics is being used. For instance, programs are being reduced in some canonical form to avoid reevaluating semantically equivalent programs that are syntactically different. And for that, of course, you need to have a specification of the operators you're manipulating. And so that's how semantics is being taken into account. And the last one, well, evolutionary search, well, that's just the standard way it's utilized. That you start with something simple and you just mutate until you get something more complex, and hopefully that fulfill the requirements. And the other thing is that we have islands of populations. But it goes back to the idea of trying to keep a diverse population of programs. We don't want just one island with just the dominating programs preventing the non-dominating programs to keep evolving and perhaps might lead to better solutions. I mean, it's basically a way to go past the maximum optima, to basically, I mean, to travel this convoluted fitness landscape that might go up and down until it reaches the optimal solution. All right, so this is a kind of a sketch of Moses. So you're supposed to see my mouse, and here we've got the meta population. So each deme is an island, and what's going to happen is that Moses is going to choose a particular island, and it's going to start to grow this island. So it's going to start with an exemplar, and it is going to define a sub-program space. And I hope you're not hearing what I'm hearing. Okay, I think my microphone is fairly limited in range, so I guess you're only hearing my voice, hopefully. So what was I saying? Yeah, so Moses is going to construct a deme by first defining a subprogram space. And basically, it's just going to map this subprogram space into a vector space. And it's going to basically change the values of the vectors that we call knobs. And it's a nice way to basically map program optimization into vector space optimization. Yeah, as I said, well, why taking into account semantics and avoiding overrepresentation, and possibly even, as it's mentioning here, meta optimizing. So that is, as it's traveling this subspace, trying to understand it and traveling the subspace more efficiently. And there's a lot to say about that. And I guess hopefully I can say a few things about this towards the end. Okay, so all right, what is that? Okay, what kind of applications? Well, we have used Moses in many domains, genomics, sentiment analysis, financial prediction as well. We even used Moses to control a virtual agent. It was doing some imitation learning and other things. So I would say that the main strength of Moses compared to traditional machine learning approaches is that the models you get are pretty expressive and very compact. And so the good side effect of that is that it gives you the opportunity to understand the model. If the model is just intrinsically too complex, well, it's still going to be hard to understand. But at least if you can avoid having a giant matrix or tensor of millions of numbers, and you can just compress that into maybe a formula, a program with a dozen operators, well, that's great. I mean, that's awesome. That's awesome for the human who is trying to understand what's going on. That's awesome for the machine who is trying to analyze this program. So I think that's really the main strength. And because it's a rather mature piece of software, it can do that relatively efficiently. About the weaknesses, well, we still are supporting a limited vocabulary. So, I mean, it's working extremely well for Boolean formulas. And it does goes beyond that. I mean, we can just do arithmetic and even some simplistic recursions, but it certainly doesn't support the full recursion expressiveness. And as I say, the meta optimization part is fairly limited as of today. We did some interesting experiments with that, but I mean, it's still at the level of prototypes rather than really well integrated and just well-rounded and working. And so for that reason, I mean, it is compared to what it could be, it's still rather inefficient. And so we want to improve that. And so that leads me to, well, perhaps the most important reason why we want to port MOSES to the Atomspace. Ultimately, we really want to unleash the full potential of meta optimization. And in order to do that, well, I mean, how do you do meta optimization in the most generic and efficient way? Well, you need an AGI for that. Well, how do you get an AGI? Well, we have OpenCog, which is a platform for AGI. And so the idea is to basically take advantage of all these growing AGI that is taking place inside OpenCog to do the meta optimization via, well, for instance, reasoning with PLN, learning with a pattern miner, or MOSES itself, etc. Obviously, we want to expand the vocabulary. And so one thing is that, well, what do we have in OpenCog? We have Atomese, which is a already pretty extended vocabulary of operators. And so we want MOSES to support that. So what I should say is that basically as of today, MOSES has its own description language, which is called Combo. And what's happening is that, so when learning is taking place inside MOSES and we want to use these programs inside the Atomspace, we have basically a converter that is just going to do the translation. But MOSES internally is using its own representation language. And if we fully port MOSES to OpenCog, well, then we can just directly use Atomese. That's what we're already doing to some extent. And the other reason is we want to be able to express the fitness functions directly in Atomese itself. So for instance, a fitness function could be, well, take this subsection of the Atomspace and try to find some patterns, try to predict some part of the Atomspace given some other part of the Atomspace. It could be about maximizing goals in some environment. It could be anything that can be expressed in Atomese, which is, well, basically anything. All right. Okay, so what do we have for now? Well, we do have Atomese as description language. We don't support all operators of Atomese, but we already support every operator that is expressible in combo, which means Boolean logic, arithmetic, and some limited form of recursiveness. We have something which is already cool, which is that now the program space is represented in Atomese, which potentially enables some form of meta-learning as to how the subprogram spaces are being defined. We have reduction. So reduction is basically taking two programs that are semantically equivalent but syntactically different and recognizing that they are actually equivalent. It's actually a fairly hard problem because it's undecidable in general. So that's another domain where we want to leverage the intelligence of an AGI. And so we have some partial progress. Basically, we have, well, some operators are supported. Well, the simplest for starter, like N or not, etc. And so the good thing about this is that once we have a reduction engine that fully support Atomese, then this reduction engine can be used not just for MOSES, but can be used for anything in Atomese. So for instance, let me give you an example in reasoning. Reasoning is basically evolving Atomese programs that represent inference trees. And these inference trees, they can actually also be semantically equivalent while being syntactically different. And of course, if you can recognize that, and if you can do that efficiently, then you're going to be able to prune the search space of inference trees. So that's a very important bonus added to porting the reduction engine to the Atomspace. And so as for the optimization, well, it's still implemented in C++, and the fitness functions are also implemented in C++. Well, of course, I mean, when I say fitness functions implemented in C++, I mean classes of fitness function. I mean, we can provide tables of data to fit, etc. But I want to say that it doesn't have the full expressiveness of what it's going to have when it will be fully ported to Atomese. And also, that's it. So that's for the end of my presentation. And if I have some time left, I'm going to make some demo. They're going to be fairly limited. I mean, Kasim would have been excellent for that, but unfortunately, he cannot be here. So, well, I'll do as best as I can. So let me unshare my screen, and I'm going to share another screen. Do you have questions so far?
So far, there are no questions, but we encourage people on the YouTube live stream to definitely ask them.
Okay.
Neil, may I ask a question?
Yeah.
Maybe. Okay. Actually, could you please provide an example of meta optimization? I'm not sure I fully understand what
okay.
is it.
Okay. So actually, I can provide you the example of what was done initially by Moshe Lux, the person who designed the initial version of MOSES. So basically, you have a program space, and you take candidates, you evaluate them, you get a score, and so you associate each candidate to a score. And one way to meta-optimize is to basically take all these candidates, split them into two classes, the good ones and the bad ones, and then you can use whatever classifier you want in order to try to predict before you evaluate whether a candidate is going to do well or not. And actually, what Moshe Lux did is even better, is that the classifier was a Bayesian net, and so he was able to basically skew the random sampling of the candidates in order to directly sample one that has a higher probability of being a good one. Okay, so does that answer the question, Vitaly?
Thank you very much. Actually, I think I need to get more information about this, looking into maybe code.
Okay. Yeah, but that's an excellent question, and there's a lot to say about this. And actually, I'm going to use this question to develop a little bit. So basically, I mean, trying to model the fitness landscape as you're searching is an excellent way to go. But it has multiple problems and challenges. For instance, in order to be sufficiently good at modeling this fitness landscape, you need to have a lot of candidates. I mean, if the dimensions are sufficiently large, you might need, there's no limit. You might need billions. And even after billions, you're still going to have some level of overfitting because, there's so much combinations that are possible when you start to have dozens of dimensions, that you never know whether your model is actually noise or is actually a good predictive model. So we come back to my presentation of yesterday, which is why do we need so much reasoning when we are doing machine learning? And the reason is that when you have background knowledge, and possibly background knowledge that you are very confident about, then it doesn't give you millions or billions of extra data points. I mean, it gives you more than that. It gives you, think about physics and, for instance, gravity. I mean, it's something that we know with extreme precision. And if you take all the cumulative observations of the physicists over the past 200 years, I mean, it's absolutely massive. And so background knowledge gives that. And then you don't need to explore, if you have that, you don't need to explore a subprogram space very extensively. You can just use background knowledge and say, well, I know that this is not going to go anywhere, or I know that this should lead to an interesting solution, etc. So that's where reasoning, PLN, and so on, and all the problems associated with reasoning and its efficiency and so on is very crucial there. And you can even go beyond that by using background knowledge to transfer the knowledge that you acquire during meta reasoning for one problem, meta optimization for one problem to another problem. So it's a very important aspect of Atomspace MOSES. Okay, so yeah.
I have a couple of questions now. So you discussed how reduct basically, the idea is to reduce it to have the same semantic meaning, but to get everything to a similar syntactic structure.
Right.
And so a question came in, could the reduction in AS MOSES eventually lead to normalized forms of representations within the atom space itself?
Exactly.
And
Yeah.
And now the other follow-up question of my own is, what would the normalized representations within the atom space look like? How much have you thought about that?
So I have thought about this to the extent that I felt the need of that as I've been using OpenCog. So it's a very relevant and interesting question. I mentioned reasoning, but actually it goes beyond that. I mean, anything that you represent, for instance, if you are controlling an agent in a virtual world, well, I mean, any analysis, any representation that the agent is going to use are going to be subject to a potential reduction. And so suffice to say that the usage is extremely broad.
And a few more. I mean, I think that's going to be actually a crucial point that we're going to have to address on that in the future, right? But the next question is, what is the performance of Moses, AS Moses, say, versus Moses at this point?
Okay, so as of today, it's about the same, and that depends on the situation. When it's not, sorry, when it's not exactly the same, at this point, it's probably due to just the lack of optimization, because at this point in the port, we haven't reached the moment where we are really going beyond what Moses used to be. And okay, when we evaluate an Atomese program, yes, it's very slow if this program is making use of a pattern matcher queries or things like that. But our programs, as of today, they don't use the pattern matcher, for instance. So the interpreter is actually, in terms of efficiently, is about the same. It's a bit slower, but it's like it's a small factor. And we actually, I mean, there are many things to say, but we actually get back the performance loss because we can use a more sophisticated form of caching, because we are using an Atomspace to hold the population of programs.
Yeah,
So
I think
point maybe to go to the panel, or go ahead, Ben.
Oh yeah, I was gonna say about the efficiency issue. I mean, there's a lot of use cases for automatic program learning, right? And we're not trying to optimize Atomspace Moses for, say, genetic programming for symbolic regression or something, where you could do that much more efficiently than in current Atomspace. And even with OpenCog Hyperon, I mean, we're probably not going to get Atomspace Moses in the Hyperon Atomspace to be as fast as a standalone genetic programming for symbolic regression tool. So I think that the use case we really have in mind is one where either fitness evaluation requires some reasoning or pattern mining or something in the Atomspace, or where you're using some probabilistic inference to guide evolution, which is using the context in the Atomspace. And if you're doing that, I mean, then the idea is that's giving a qualitative increase in the speed with which you're getting an answer. And if you're using the knowledge in the Atomspace, either for fitness evaluation or for guidance of evolution process, I mean, then it's just clear you want to be in the Atomspace. And for Reduct, there's a lot of subtlety also, because the normalization of programs into elegant normal form is kind of straightforward for, say, Boolean functions or for arithmetic functions in symbolic regression. But if you have higher order programming constructs and you're trying to then normalize them into an elegant normal form, there may be a lot of ways to go to do that reduction, and then being able to do a little more inference, which the Atomspace supports, is going to be a big help. And that's part of what drove us to push toward Atomspace Moses. Is like we wanted to reorganize Reduct in certain ways, and then we realized, well, shit, we're like building a whole inference engine. We're going to be rebuilding a new inference engine inside the Reduct library, inside Moses. But that's kind of what Atomspace is for, is to have flexible, implementation of various inference engines. If you're going to make Reduct into a whole inference engine, maybe even a probabilistic fuzzy inference engine, then we really want to be doing Reduct inside the Atomspace, and then we might as well be doing Moses inside the Atomspace. So it's a little bit similar to some of the comments I made about the Atomese interpretation, right? Like, we're not going to make Atomese language the fastest possible way to write a word processor or to implement the fast Fourier transform, and we're not going to make the Moses the best way to do symbolic regression with genetic programming. But if you're looking at the requirements for a programming language interpreter or an evolutionary learning system in an AGI context, then you're looking at a context where a lot of what the individual process is doing is drawing on the broader context in the atom space, where and that's a different it's a different set of requirements than for standalone tools. And this is a broader point. Like this gets at why you can't just make a hybrid integrative AGI system by taking like best of breed AI components and wiring them together. I mean, it's because it seems like you could do that, but actually the optimizations and specializations you make for standalone activity are different from the optimizations and specializations you make when you want to use an algorithm in a cognitive synergetic way, where its intermediate states are making use of the contributions from other algorithms. And we see this broader point pop up over and over again in each specific component that we talk about.
I can ask some more questions, or should we go to the panel at this point?
We might as well go to the panel, which will just be like more asking questions, but with the whole group explicitly participating in it.
Okay, so so that's you, Ben. It's you, Nil, Alexey, Cassio, and I guess Linus. Is he on here? Yes.
Yes.
If he's on here, I'm happy to have him join the panel though. Yeah, I see Linus on the. So Linus, to join the panel, you have to just unmute your video and audio, basically.
I've sent him a request to start video, but maybe he is getting a cup of tea. So perhaps we can just take like one more question, and when everybody's ready, we can just hop into the.
Well, we can just activate the panel, and Linus can join the panel once he's ready. That's fine. Ready.
Linus unmuted his video.
Oh, that means Nil and Cassio should also. Yeah. All right. Cool.
So, I mean, right now I'm just thinking Moses, so I have those, but this is the panel on basically the version OpenCog Hyperon steps towards that. So we heard quite a bit, and I think that one of the things, and I was going to ask that question, and I think Ben, you already kind of brought it up, the whole cognitive synergetic aspects, and how all these different pieces and redoing the different pieces, the atom space, which is very closely tied, as Alexey brought up, to the actual Atomese language, to how Moses interoperates, AS Moses interoperates with more directly the atom space, allows for better cognitive synergy by making it easier to interoperate with PLN, or the Economic Attention Network, CCAN, or natural language processing. So with all of this in mind, there's a lot to think about, because any changes you make in one part obviously are going to have ramifications in a certain manner with other parts of the OpenCog architecture. So I guess the question for the panel, I mean, obviously the atom space is the kind of the heart of the whole thing. How do you limit those ramifications and make it easier to think through all the use cases you wanted to implement in hyper?
Well, I think this took decades, right? I mean, if we go way, way back, which you like me are old enough to remember. I mean, in the WebMind AI design, which came before Novamente AI design, which came before OpenCog AI design.
Each one being
WebMind, it was really more like a distributed, weighted, labeled hypergraph, where we just had like any old AI algorithm in there, and they were just supposed to interact in a pretty flexible way, and it would all come out in the wash, right? And one of the things we realized from the chaos that ensued was that you really needed to think hard about each AI algorithm that you're implementing, and what are the semantics of the nodes and links that it's using, and how can you translate between the semantics of the nodes and links one AI algorithm is using and the semantics of the nodes and links the other AI algorithm is using. And there wasn't necessarily a magic shortcut to that. I mean, it's a bunch of different cases, and it's subtle. I mean, I think there's some common aspects to it. I mean, in WebMind, not all the algorithms used a probabilistic semantics, right? I mean, we had Pei Wang's NARS in there, which is non-probabilistic uncertainty, and we had some genetic programming, but we weren't using Moses, which does probabilistic modeling of the programs in the evolving ensemble. So I mean, one shift that happens as we went to refine the different algorithms cooperating together is a focus on probability theory as one of the common elements of this semantics. But then you also have fuzzy logic in there. And I mean, Nil and I, together with Cassio and others, spent quite some time working on how do you get probabilistic truth values and second and third order probability distributions to work together with fuzzy values and fuzzy values of probabilities and probabilities over fuzzy values. And I mean, there's just a lot of work there.
Common sense reasoning.
Yeah, there's a lot of work in reconciling these representations, and we haven't focused on that so much today because we've been talking more about like the shift from current OpenCog to OpenCog Hyperon doesn't change these things, right? Like that's more in the math and the logic of the representations of PLN logic or of Moses or of, say, ECAN attention allocation. Again, what makes ECAN that's spreading attention different than just an attractor neural net spreading attention? Well, there's a probabilistic semantics to short and long-term importance and short and long-term attention values, and that probabilistic semantics in ECAN allows ECAN to interact meaningfully with the other AI algorithms there. So there's really been a lot of thinking underlying how do we get these different kinds of learning and reasoning algorithms to be semantically coherent with each other so that cognitive synergy can work. And a lot of this is written up in engineering general intelligence, real world reasoning, and a whole bunch of research papers. Alexey has contributed a bunch of original thinking there regarding how probabilistic programming and how some modern neural net architectures like Infogan and so forth, which have a probabilistic programming aspect, how they also are semantically consilient with these other methods that are running in Atomspace. And all this from an OpenCog Hyperon point of view, it's content, right? That's about the cognitive content in the Atomspace. And we sort of have all that there from decades of work on this. What we've been missing, I mean, among other things, is an infrastructure that lets us really play with these things at massive scale. And that brings us back to the analog with what frameworks like Torch and TensorFlow and what massive GPU servers have done for deep neural networks. I mean, I was teaching multi-layer perceptrons, like deep neural nets in the 1990s, and recurrent backpropagation took like all day to run on a recurrent neural net with with a few dozen neurons in it, right? And now that you can scale this up, all of a sudden, a lot of these things work with fairly minor algorithmic adjustments. So what we're looking at with the OpenCog Hyperon refactoring is like, how do you make something with the needed scale to let all this funky mathematical thinking about cognitive synergy to actually strut its stuff appropriately.
Linus, were you trying to chime in there?
Yeah, Ben sort of hit on, well, I mean, Cassio mentioned something called chunks, and Ben is sort of dancing around this. I've taken several attempts at doing a distributed atom space, and the number one most difficult aspect of it was dealing with the correct chunks of the data, of defining a glob of data that moves together from one space to another. That's what I needed to move from one computer to another. That glob is something that I need to process all together with the same kind of an algorithm. Finding and defining the boundaries of that chunk were the main blocking point for applying any kind of algorithm that I could think of, or just simply moving that data from one computer to another, dealing with distribution. And I feel this is also has been sort of a neglected part of thinking in OpenCog, is how we deal with a collection. I mean, for example, look back at the brain, right? What does the brain do? Well, it's not just this it's not just this homogeneous mass, right? There's a visual cortex which is working with that chunk of visual data, and it has a high bandwidth connection to another part of your brain that deals with 3D positions and locations. But it's not attached to your language, not naturally. I mean, the bandwidth between, the part of your brain that deals with language is somewhat weakly and poorly attached to the visual part, which is, it's adequate for us. But this is what I mean by chunks. There's a language chunk, there's a visual chunk. How do I pull those apart? If I talk about the atoms, a distributed atom space, how do I say, here's a chunk of atoms dealing with this part of genetics or genomics, and it maybe should travel together as a group, as a distinct group from, say, some other collection of atoms that describes proteins, because right now you're interested in genes, not the proteins. How do I group these things together into coherent units? And it's answering that question has been, for me, the number one stumbling block for a distributed atom space, for example.
Cassio, you have any thoughts on that?
Well, first, yes, this is obviously the key question, and if you don't have a halfway decent answer to that, then there is no hope of a distributed atom space ever performing reasonably well, right? There's a couple of extremely early, partial, and not at all satisfactory thoughts here. I mean, they're not by any means a complete attempt at a solution. But there's two things. The first one is we're mostly thinking about DAGs. We're most thinking about DAGs that have a root, so to speak. The root could be an evaluation link, it could be an execution link, it could be a bind link. But very often you're going to have, a couple dozen nodes that they are linking through a structure that looks like that kind of DAG. And there you have small chunks that go together. You don't have to worry about whether they're biological chunks or language chunks or vision chunks. You just know that structure is there, and there's patterns that in that kind of structure that lets you kind of search for it. So that's part number one. Knowing that there is a gigantic collection of small DAGs is somewhat relevant here, right? The second one is, I think, a lot of the patterns you want are going to be application specific in the beginning, and of course that does not solve your 10-year down the road problem of which chunks are relevant in an AGI context, but hopefully by then you've been able to build a large enough data set of which chunks are meaningful and which ones are not, that you can train your way out of this. But what Senna was playing with in early prototypes was, there's a pattern index. Every pattern matcher answer that gets returned reasonably frequently becomes a chunk that's worthy of being distributed, and users can define templates that they want. Everything that matches this template should be distributed as well. Meaning it should be replicated.
I think, like, if we look at the biology use case, as you say, in that use case, it's sort of clear how you would chunk things, because I mean, you have data from gene ontology and from pathway databases and so forth. So I mean, you can take all data about a certain gene or about a certain process like apoptosis or something, and you know these are connected to each other and are going to pop up in answers to the same queries. Now that's sort of cheating from an AGI context, right? Because these are structured ontologies about a structured domain of molecular biology. But for that application, it works reasonably well. Now, if you were dealing with, say, a Sophia robot that meets a lot of people, there's also a lot of domain-specific heuristics, like all the information about a certain person or a certain place. I mean, that domain, like everything about Linus Vepstus. Okay, everything within a few links of that guy, we can treat as a chunk. So if I was going to try to do something more general, I mean, what has occurred to me is this is very similar to what in engineering general intelligence I called, map formation and map encapsulation. Like just for concept formation processes, I wanted there to be an AI process that would look at like which collections of nodes and links are important at the same time and tend to be used in the same context. And I mean, that's important because those may have some conceptual connection. You want to group them into a common concept. Now that's not quite the same thing as a chunk that you want to move around concurrently in the distributed processing context, but there seems to be some relationship there. Like it seems like there's a need to develop fast, lightweight, and sort of okay methods for identifying, sub hypergraphs that have some coherence with each other, and maybe with a certain tuning, that method is useful to find chunks that are coherent for distributed processing. With another tuning, that process is useful for finding concepts that are useful for feeding into reasoning. And this is a research area that somebody needs to undertake now, right? But of course, everyone's busy.
Yeah, I would describe these things in a slightly different way, but basically the idea is the same. If you don't have a complete solution now for AGI, and we certainly don't have, then make it programmable in Atomese, and then make it self-programmable or inferable. So I guess this general pattern which we are trying to follow.
Okay, so I have a couple of related questions. Have you thought about integrating an ethics module deep into the system in the new version when the system itself learns from proofs in the future? And related to that, with OpenSci, how do you prevent the system from going in the wrong direction? For example, Microsoft's Tay disaster.
Well, I mean, the Tay chatbot was just a chatbot with no understanding of the semantics or meaning of the words it was saying. So someone said, Hitler, Hitler, Hitler. It just said back, yeah, Hitler, 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 but it didn't know who Hitler was or what it meant. So that probably illustrates a whole bunch of other problems. Like how did a $1 trillion corporation not realize that putting a chatbot to learn from random people on the internet would lead to a instantaneous time to penis, right? But I mean that's that's a whole other set of problems. But I think as far as an ethics module, I mean, my own view on that, and others may have different views, but I mean, I think ethical behavior it's cross-cutting on the level that we're talking here, right? Like I don't think ethics is a separate module. I think ethical behavior is something that cuts across all the different kinds of learning and reasoning that we're talking about a mind doing. And what you want is to be sure that your system has a rich enough set of representations and learning and reasoning mechanisms that it's able to learn human-like ethics from experience in a genuine way, which requires abstraction and grounding of those abstractions in experience, which is, I mean, of course, a textual chatbot like Tay has no effort at those things. In terms of OpenCog goal system, it's true, you know, the OpenCog requires you to specify some top-level goals. I mean, it can be a number of top-level goals. It doesn't have to be one top-level goal, but it requires a number of top-level goals. And the system is then trying to learn which procedures will imply achievement of those goals based on the current context. And there's formulas then for action selection based on the weighting of the importance of those goals in the current setting and the degree to which the actions will imply achievement of the important goals in the current context as estimated by reasoning and so on. And you can have sub-goal learning where the system learns which goals imply the top-level goal, but top-level goals in the current code base, I mean, they're supplied by the human programmer. Now, it's important that not all activities in the system need to be goal driven, right? I mean, you can have a process that's just doing background inference and learning new nodes and links, and the nodes and links that it learns may be used for goal achievement, of course, but it's not 100% goal oriented in the sense that some simple reinforcement learning systems would be. But indeed, if you chose the wrong top level goals, then you may get a system doing something nasty. Or if you choose goals that look right, but the system revises all its nodes and links so it reinterprets that goal in some way utterly different than you expected. I mean, this could also lead to a bad outcome. I think the code framework also allows a fundamentally developmental system that will create new top level goals and put them at the top of a goal hierarchy. I mean, one could write something that said, like, any newly formed concept which meets certain parameters and is important enough and interesting enough, certain newly formed concepts could be popped up to the top as new top level goals. Then you'd have a system that was fundamentally developmental and was inventing its new own goals in a sense. So there's a lot of flexibility there. And I think the capability is, in my view, there for the system to learn human-like ethics if it's in an appropriate context where it's cooperating with people in environments where it can see people carrying out ethical or unethical behavior, and it can receive guidance from human teachers. But there's certainly nothing in the architecture that guarantees someone couldn't train a psycho killer OpenCog also. And that's kind of like the human brain, right? I mean, there's nothing in the brain architecture that intrinsically prevents you from training a human to be good or nasty. A lot has to do with the education and the environment.
Well, I want to talk briefly about what you've been calling the global brain, right? And then the issue of social media, right? You get onto places like Facebook where groups of people can convince themselves into certain types of viewpoints. I mean, these days they tend to be political viewpoints, but they can talk themselves into believing all sorts of rather strange things, which you can arguably say are unethical, especially if you're coming from the other political viewpoint. And so now if you look at these individuals, you say, okay, well, they're agents, they're thinking about things, they're processing their little corner of the world, and yet collectively a group of 100 or 1,000 of them have decided that killing this or taking that action is the right thing to do, and yet from the broader base of humanity you say, well, no, that's very highly unethical, right? So in a certain sense we have the same problem with AGI. Now we're talking about AGI again as if it was a singular individual thing, and it's not really that. It's really a bunch of different algorithms. We're looking at different parts of the data, seeing only part of the picture, and communicating. And to some degree, I mean, the AGI of the future has to be part of social media. The AGI of the future has to show up on Facebook and talk to everybody all at once. It has to be part of this global conversation. And the ethics develops there, where you're going to have, you know, tens of thousands of people shouting it down saying, no, 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 saying Hitler 3 times is a really bad idea. Or, you know, they may say some political viewpoint is a really bad idea. You know. Well, let me rephrase that. What's politics, right? Politics is exactly those sorts of issues about which we have very little scientific, rational evidence. They're all issues about which we can't really apply the usual scientific process to determine truth or falsehood, to determine how well it aligns with reality. So instead, people just form opinions and throw them out there, and then they argue violently about this because you can't settle the debate. You can't build a scientific instrument that will prove that, you know, that this is the right answer and this is obviously wrong. I mean, for flat Earth, I guess you can, so that's a separate issue. But this is the fundamental problem of ethics, is that, you know, if you just give a bunch of people and let them wander off into a corner, they'll conclude any kind of crazy ethics you might, you know, think of. And there's some risk that AGI detached from humans will wander off the same way, and with algorithmic propaganda, take the humans right along with it. So it's a tough issue. It's it's at the very lead of things. And yeah, no, to agree with Ben, no, it's not modular. It can't be modular.
So looking at this another way, are there parts of the OpenCog architecture that are self-referential in any way? Will OpenCog be able to extend itself by writing Atomese or in some other way at some point in future versions?
Yeah, I mean, this is one of the reasons that we're interested to sort of refactor parts of Atomspace or the whole thing. I mean, Nil and I have already been doing some work with trying to use pattern mining and reasoning to learn new inference control strategies. And I mean, Alexey and Vitaly and some of their colleagues in St. Petersburg did some work using neural nets to learn new PLN inference formulas, like more optimized logic inference formulas. So there's been various efforts at this sort of meta level reflective learning. And there was a workshop on self-programming at one of the previous AGI conferences where I talked a bit about self-programming in OpenCog, and also Kristen Thoresen gave some very interesting discussions on self-programming in ERA and Replicode and their cognitive architectures, which was somewhat inspirational for the cogistry, algorithmic chemistry idea, which we never have yet implemented much in OpenCog, but I've discussed a couple of times. So that aspiration is certainly there. I mean, in terms of the software engineering level, I mean, in practice, we're looking at how to make it highly efficient, scalable implementation, which would be C++ or Rust or whatever language seems optimal, but it's going to be some low-level language designed for optimal implementation of these highly scalable operations. And we're not going to see OpenCog like rewriting its C++ or Rust lower level code anytime soon. Like not until we're at human level AGI, I would imagine. But within the atom space that's created using this lower level code, we absolutely want the learning and reasoning processes to be learning new reasoning algorithms, new learning algorithms, new inference rules, and so forth. And I mean, you can make an analogy there to the human brain, right? The human brain is, we're self-modifying our knowledge in many ways, and we're rewriting our own ways of thinking. On the other hand, it's very rare that I rewrite the way, say, my glutamate receptors process glutamate coming into them between two neurons in my brain. Like there's a certain infrastructure there that we're not yet screwing with. Now, it's cool that ultimately the AGI can screw with that, right? Like it'll be easier for a human level AGI OpenCog to rewrite its C++ code than it is for a human level AI Ben to rewrite his glutamate receptors, right? So that there is that potential there in the long term, which is really cool. But the earlier stages of reflection and self-modification is more within the atom space hypergraph process soup, which is going to be made scalable by a bunch of lower level code that the AGI isn't going to know how to deal with till it's human level.
Okay. So another, how is OpenCog going from reasoning and predictive data modeling to autonomous decision-making and synergetic activation protocols?
I think that's OpenPsy, right? I mean, there's an explicit motivational system that we already discussed. I mean, you need a system that says, hey, here's the goals, and now you need a cognitive cycle that has the system iteratively trying to choose actions that will achieve its goals based on the context. And there's a lot of subtleties there about goals on different timescales and how to balance them. But that component is there. And I would say, take a look at Joe Shabak's book from like almost 10 years ago, Principles of Synthetic Intelligence, which is from his PhD thesis. And Joe Shabak in that book outlines the principles of the micropsi motivational architecture, and that we're not doing exactly that in OpenPsy, but it's sort of a descendant of that, which was a descendant of Dietrich Dorner's psi model of human motivation, which came out of cognitive psychology in Germany.
Yeah, I would add that the good thing about OpenCog is that because uncertainty is, has a representation out of the box, it's fairly easy to basically balance exploitation versus exploration in the decision making. Yeah.
Okay. Here's a very broad question. What is the current challenge in making AGI a reality? I would add maybe what is the largest, the biggest.
Yeah, there's a lot of. I mean, I guess the way I view that is, I want to make massively scalable, very fast system to allow us to experiment with a whole bunch of ideas that we are now prototyping and tossing around on a larger scale, and then we may see what the real challenges are at that point in time. Like with something like cogistry for algorithmic chemistry, or using deep neural nets to guide PLN inference control. I mean, looks good conceptually when you write down the math. What obstacles you run into once you do it at scale, we don't know yet. I mean, any more than the current obstacles with deep neural nets were known 10 years ago before you tried large scale implementations of them.
Yeah, that's definitely true. But if we would like to be slightly more concrete, then we can say something about inference. I mean, efficient, yes, general inference. As I mentioned at the end of my talk, and we understand some things about it, like that we need the possibility of AGI engine to produce different strategies, both domain specific and sort of meta-heuristical to different kinds of problems. And this requires a sort of meta-inference, meta-computations, and so on. And this should be somehow coordinated on the level of knowledge representation. And we have some maybe mathematical or computer science questions to be solved, like what maybe the basic computational model which should be behind this type of knowledge representations, which will allow us doing and experimenting with these things. And of course, for these experiments, we will need to have a really scalable platform. At least at the current moment of time, personally, I'm looking at sort of unification of different inference methods in a sort of framework which could be quite flexible or tunable in different ways. So we can represent inference strategies, inference engines declaratively and self-applicably. So something like that. Maybe it's not, of course, it's not the whole story, but if you ask about the largest question, nearest question, maybe that's one for me.
So, and I think this is a question we should address. I mean, maybe it wasn't clear from some of our prior discussion. So how are we using recent advances in deep learning within OpenCog? Because I know that this is important in terms of our refactorization right now as well.
Well, yes. Okay, go ahead.
No, continue.
Yes, we have already mentioned both Ben in his talk, and then I also mentioned a little bit that well, our team in particular spent last 2 years exactly on this topic, not only on this, but on this in particular. So as I mentioned, Anatoly Belikov implemented cognets, which embed Atomese and unified rule engine functionality into Python, so you can natively mix up deep learning models and calls to pattern matcher and the unified rule engine. And Vitaly Bogdanov implemented grounded object nodes, which do this from the OpenCog side. So you can embed calls to deep neural network models from the Atomese. So these are complementary things. And you can use these tools for example, to construct deep module networks on fly in the course of reasoning instead of using some hard-coded imperative execution engines to assemble modules into a module network. And you can do a lot of different stuff. Ben mentioned, for example, as a possibility to use deep learning approach, basically backpropagation implemented in deep learning libraries and frameworks to train truth values. If we represent them as tensor truth values with, say, PyTorch as backend. So in the course of reasoning, we managed to implement this in such way that computational graphs, PyTorch computational graphs appear not broken, so we can do end-to-end training, and yeah, this basically gives us the possibility to use recent advances in deep learning inside OpenCog. So it's not just a naive hybridization when you take deep neural networks outputs, transform them into Atomspace, and then separately reason over them in OpenCog. But it's really a very flexible hybridization. And there were other research directions like vector embeddings, graph embeddings, which were described yesterday. And yes, we are thinking about how to do it even better in OpenCog Hyperon, but it's a separate topic for discussion.
I was going to bring up the bio talk yesterday, and I know it's an informing part of also the redesign, as well as how to basically integrate such systems within OpenCog. Another question, what would you say is reasonable amount of time / person size to accomplish this mission? We need an AGI for that, right? To figure out how long it's going to take to create an AGI.
I mean, there are many aspects to the mission. I mean, I think for a largely software-oriented part of it, like say engineering a new version of Atomspace and associated infrastructure, which we're calling OpenCog Hyperon. I mean, for something like that, you know, we can proceed to more thoroughly enumerate requirements. We can write down an architecture, and then at least there's some basis to estimate how long it will take to engineer something like that. And of course, there's a motivation not to have the answer be 10 years or something, right? I mean, if it's a year to implement a new infrastructure for an AGI system, I mean, that's reasonable. If it's 5 or 10 years, your design is too ambitious and complicated. So so I mean, we're going through that process now of requirements and design, and then we'll be able to make a serious estimation. I mean, it's not going to be a few months. It's not going to be many years. If there's a year of implementation work, I'll be happy. This is hard stuff. But then to get the actual AGI to work at human level intelligence, of course, that depends on how a whole bunch of coordinated research projects are going to pan out. I mean, what I could say is, in my view, we're at a stage now where, years rather than decades to human level AGI is a plausible possibility. Like there's no huge and obvious blocker there that absolutely couldn't work. Like if you ask me how long is it to a quantum computer based AGI, the answer is different, right? Because there's sort of foundational engineering work that has to be done. You're not going to get there in a few years. And here we have some theory that seems to make sense. We have a whole bunch of prototyping and experimentation that we've done already. We have, the inklings of a design rapidly being fleshed out for a more scalable and easy to use implementation. And then we have to see what happens when we scalably deploy a bunch of this stuff that we've prototyped, and there's a bunch of research to do there. So I mean, could we be a few years from a human level AGI? I mean, it is certainly a possible thing. Could we hit some hidden rocks along the way? Of course, also quite possible, and we don't know what those are going to be.
Okay, thank you. Anybody else want to chime in on that, or?
It's just a few years. That would be truly magical.
Yeah, it would be magical. But I guess if we look at the time between self-driving cars or face recognition being considered almost impossible, and them being like routine technologies that everyone just assumes are part of the plumbing of life. I mean, this was years. It was years, not decades, right? And the ideas were old, right? The core ideas were old. What happened is infrastructure was scaled up. Then a bunch of it's not like deep neural net code from 1966 was just run on a GPU and it immediately let face recognition be on every camera in Shenzhen, right? I mean, the hardware got faster, then frameworks were made that exploit that faster hardware, then the familiar algorithms and concepts were tuned and refined by a lot of very smart people working hard. But there was still like a few years of transition from basically doesn't work to wow, this works, we're gonna roll it out everywhere. Now if my intuition is correct, we're at that point with regard to these integrative AI concepts and getting a scalable infrastructure for all the ideas we've been working on for so long is going to enable an exponential leap in functionality for what we're doing, similar to what you saw with deep neural nets as you got these scaled up onto multiple GPU servers. And that's we've seen it in recent history in AI before, right? Just like in the last 5 to 7 years, right?
It was certainly Moore's law has a habit of catching everybody off guard. I mean, you turn around and all of a sudden your computers are 2, 4, 6, 8 times faster. And oh wait, the 6 didn't belong there, right?
Yeah, and things that everyone thought were impossible are now considered obvious, and they expected them all along. I mean, this happens again and again.
So one thing I would point out is there's a lot of pieces that took many years to figure out and then implement. And those are largely completed or nearing completion, at least in terms of the first versions. I'm thinking PLN, I'm thinking Moses, ECAN, all of the, some NLP, all of the different pieces have been completed. Which wasn't the case.
I dislike that completely because if I look at things like PLN, I can there are many functional issues that I have with the code. I keep my lips zipped because I don't want to create brand new arguments, but I see a whole new different ways of writing and restructuring that stuff so it works differently, faster, better, more general.
I don't disagree.
We're not done there.
But when I first started, there was no PLN.
In that sense, things have dramatically improved.
There was no Moses. There was no ECAN. None of those pieces existed, even conceptually.
I want to call those versions 0.1. And I mean, similarly for any linguistic subsystems, we've got a 0.1, we've got a sketch, it seems to work, the proof of concept is there, but it's still quite easy to see brand new and better ways of building all of these things. And now comes the mythical man month of how many people does it take to build something better, and how do you get a large group of people to communicate and agree on what the goals, what the project development goals are going to be, and how we're going to allocate those resources to build version 1.0. It's that,
and then connecting,
stumbling block.
Connecting and integrating and tuning.
Yeah,
I mean, there's still tons to do.
This gets into more project organization issues, right? Because I mean, obviously, as I mentioned in the introductory versions of both of my talks, I mean, OpenCog, it's been an amazing sort of thinking and research and prototyping playground for a relatively small group of us. And we've had a broad group of people communicate off and on to the code base, contributing cool fixes and patches and stuff here and there. But obviously, it hasn't grown into the huge flourishing OpenCog open source community that we all would have liked it to. And partly that's just because we're dealing with some very hard problems here that not that many people want to put their brains into thinking about, and partly it's because we didn't develop it with like a clear practical use case right from the start. Although we've used the code for various practical things on the back end of various systems, but I think now, now that the times have changed, AGI is much more popular now. There's broader interest in the sorts of things that we're trying to do and have been trying to do for a while. And due to computers being faster and there being better supporting software code of various kinds, things can be a little less sluggish and frustrating than they have been at times in the past. Like my hope is that by starting an initiative to rebuild some things for greater scalability, my hope is in this context, we can do a better job at pulling a community together than what we did before. And of course, that's a hard thing to do in itself also, but at least I think the timing is on our side. And Linus, who we have here, has been involved with Linux development for quite some time, right? And there's been a lot of developer hours put into Linux, and in a interestingly decentralized way. Like, you have a kernel team, but then you have all sorts of other pieces being built by different people all around the world, and no one had to organize or pay all those people in a unified way. It was quite complex how it came about. And AGI may end up being more like that. If we look at what I'm trying to do with the new OpenCog Hyperon version, clearly we need a small team of 10 or fewer amazingly good developers just working together tightly on building some core code of a Atomese 2 or parts of distributed Atomspace. But that doesn't have to be everything. Like we need to pull in a much broader open source community to contributing different parts to this thing, or there's going to be too much for it to be done outside of a big tech company, which is obviously the way we're trying to do it.
Well, the Linux kernel succeeded because it did have a clear use case, as it were. I mean, operating systems were known. You had to do that, what an operating system does. And it also had a clear-cut API to it, right? There were, some 50, 100 odd dozen, 50, 100 system calls, and that was the API. The C libraries built on top of those system calls, and every other application from the GNOME desktop to the KDE desktop to the Android phones, right? They all sit on top of those about 100 or so system calls that the kernel provides. And those have been frozen in ice for what, 20, 30 years, however old, 25 years, however old the Linux kernel is. They just simply don't change. And that allowed lots of work to happen under the covers, and it allowed lots of work to happen up above it. But that API in the middle between the kernel and the user space has remained fixed. And I think you need something like that for stability. You need those sort of stable things that all the programmers can work to. Well, okay, so you can argue, yeah, the Atomspace provides some of that, but what are we going to keep stable there? Okay, I talked about shared vision. I talked about PLN briefly and ways of, for instance, looking at better ways of looking at things. I talked about the connectors and connector sequences. They look just like atoms. I'm not clear that I've ever gotten the message thoroughly across, but I think this is a new and better way of envisioning how things should be constructed. I want to reverse engineer the entire atom space to be built on top of these connectors. If you start building things like the distributed atom space too soon, oh, well, you might end up building on top of an earlier, older, not quite as functional subsystem for representing your data. These are real issues. Well, it wouldn't be an issue if we had some sort of layer in the middle that says, okay, this is it, this is stable, this is what you are, the function that you are guaranteed to have, and developers can go off and use that.
Yeah, I think it's going to be key to, define the APIs for distributed atom space and define the APIs for like simple static pattern matching across the distributed atom space. And these things, if we can't nail that down in a way that we think can be stable for some time, then we're kind of screwed, right? And then as Alexey was talking about the syntax and semantics of an Atomese 2.0 language, we have to nail down what is that base language. And then, we may define we're going to define a lot of types within that language and sub-languages within that language, but we have to nail down what is the base language that we want from a next generation Atomese. And then part of that, of course, will be how it invokes the API for static pattern matching against the distributed atom space. And I think if we can nail some of these things down in a precise way that builds on what we've learned with all the work we've done so far, then that's a position from which we can, summon up developer energy from a broader pool of developers, both under the hood to make these things, performant in the various ways they need to be, and then using these tools to experiment with and improve on both the AI tools we have now and new AI tools fitting into the framework that we haven't imagined yet. And yeah, I guess we're close to the time when we're supposed to wrap up this event. So I want to, for everyone who's not that we have to wrap up instantly, but let me say, for anyone who's viewing this either in real time or afterwards, because the video is going to be sitting on YouTube for a while. If you want to get engaged with OpenCog work ongoingly, so there's an OpenCog Google group, there's an OpenCog Slack, which has like 400 or 500 people on it now or something. The Google group has even more. There's and Linus may not be on it, I don't know, but yeah. There's
Every time I get on
OpenCog wiki site, which has lists. Some of it's out of date, some of it's up to date, but there is a list of the Google group and the Slack on there. And I mean, all of us are making this up as we go along. Some of us have some experience making this shit up together for a while, but still, we're, in spite of having all these years and decades behind us, you know, we're still reinventing this as we proceed. And we very much welcome folks with you know, appropriate mental wizardry and technical background joining us in making this up as we go along, and like help us make up the next phase. Like, this is obviously a big thing we're trying to do here, both in terms of the grandeur of the goal of human level AGI and just the sheer number of pieces and amount of technical work that's involved. So we are actively soliciting folks not only to code stuff, but to, you know, think through all the issues and design stuff and help articulate requirements and all the rest. So yeah, please